What lies beyond the edge of everything we know? It's a question that has haunted humanity since we first gazed up at the night sky. I'm your guide on this journey to explore one of the greatest mysteries in all of cosmology. What might exist beyond the edge of our universe? When we talk about the edge of the universe, what exactly do we mean? Is there a physical boundary, like the edge of a table, where space simply stops? Or perhaps a cosmic wall beyond which nothing exists? The truth is both simpler and far more mind-bending. The universe as we understand it today is a vast, expanding fabric of space and time, filled with billions of galaxies, each containing billions of stars. Our home, planet Earth, orbits just one ordinary star in one spiral arm of the Milky Way galaxy. From this tiny cosmic perspective, we've managed to peer outward across incredible distances, using increasingly powerful telescopes and instruments to map what astronomers call the observable universe. But here's the fascinating part. The observable universe is just a fraction of what's really out there. It's like being in the middle of a vast ocean, where your visibility extends only to the horizon. You know there's more ocean beyond that horizon, but you can't see it from your position. In cosmic terms, our horizon is defined by light itself. Light is the fastest thing in the universe, traveling at approximately 300,000 kilometers per second. Yet despite this incredible speed, the universe is so immense that light from the most distant regions has been traveling toward us for nearly 14 billion years, since the birth of the universe itself in the Big Bang. This means there's a fundamental limit to what we can observe. We can only see objects whose light has had enough time to reach us since the beginning of the universe. Anything beyond that cosmic horizon remains invisible, and as far as direct observation goes, unknowable. But that doesn't stop scientists from theorizing about what might lie beyond. Could there be regions of space with different physical laws? Might our universe be just one bubble in a vast cosmic foam of other universes? Or perhaps space continues endlessly, with infinite galaxies and stars spreading out in all directions. The mystery deepens when we consider that the universe isn't static, it's expanding. And not just expanding, but accelerating in its expansion, pushed by a mysterious force scientists call dark energy. This means that with each passing moment, more and more of the universe is slipping beyond our cosmic horizon, becoming forever unreachable and unobservable. Think about that for a moment. There are galaxies whose light we can see today that future civilizations will never be able to observe, because the expansion of space itself will have carried them too far away. These galaxies aren't moving through space faster than light. That would violate Einstein's laws of physics. Rather, the space between us and them is stretching so rapidly that their light will never reach future observers. This concept challenges our very notion of what it means for something to exist. If we can never observe or interact with regions beyond our cosmic horizon, in what sense are they real? It's a question that bridges physics and philosophy. Some of the greatest minds in human history have grappled with these questions. Albert Einstein's theory of general relativity gave us the mathematical tools to understand the universe's large-scale structure. Stephen Hawking's work on black holes provided insights into the nature of space and time at their most extreme. Today, thousands of astronomers, cosmologists, and physicists around the world continue this quest, using everything from space telescopes to underground particle detectors to piece together the cosmic puzzle. The search for understanding drives us to build more powerful instruments. The James Webb Space Telescope, with its giant golden mirror, peers farther into the cosmos than any previous human-made device. Gravitational wave observatories like LIGO detect ripples in space-time itself, giving us a new way to hear cosmic events that might otherwise remain invisible. Enormous particle accelerators probe the fundamental nature of matter and energy, helping us understand the conditions of the early universe. But perhaps the most powerful tool in our quest is human curiosity itself, the desire to know what lies beyond. Beyond the next hill, beyond the ocean, beyond our solar system, and yes, beyond the edge of the observable universe. seems hardwired into our nature. It's the same curiosity that drove our ancestors to explore uncharted lands, that inspired the first astronomers to map the movements of the planets, and that now compels us to send robotic explorers to distant worlds in our solar system. As we embark on this journey together, we'll explore what current science tells us about the universe's structure and its possible boundaries. We'll examine competing theories about what might lie beyond what we can see, and we'll consider how future discoveries might reshape our understanding. The edge of the universe isn't just a physical concept, it's the frontier of human knowledge. And like all frontiers, it beckons us forward, promising new wonders and discoveries for those brave enough to venture toward it. To truly understand what might lie beyond the edge of the universe, we first need to understand what the universe actually is. Let's begin by exploring the cosmic scales involved and how astronomers have mapped the observable universe surrounding us. The journey from our home planet to the cosmic horizon takes us through realms of space and time that challenge the imagination, and it all begins with a single step into the night sky. The concept of an edge to the universe is deceptively complex. When a child asks where the universe ends, they're often picturing something like the edge of a map, a clear boundary beyond which there's simply nothing. But modern cosmology suggests something far stranger. Consider this. When ancient sailors feared falling off the edge of the Earth, they were wrong, not because there's a barrier at the edge, but because the Earth has no edge. It's a sphere. Similarly, the universe may not have an edge in the way we intuitively imagine. This raises profound questions. If the universe has no edge, is it infinite, or could it be finite but boundless, like the surface of a sphere, where traveling in one direction eventually brings you back to your starting point? Both possibilities challenge our everyday intuitions about space. Even more mind-bending is the relationship between space and time. Einstein showed us that they're interwoven into a four-dimensional fabric called space-time. The massive objects in our universe, planets, stars, and galaxies, create dents and curves in this fabric. These curves manifest as what we experience as gravity. This warping of space-time plays a crucial role in understanding the universe's structure. Near extremely massive objects like black holes, space-time curves so severely that not even light can escape. Could similar effects occur on a cosmic scale? Some theories suggest that the entire universe might be curved in ways that fundamentally affect its large-scale structure. Speaking of black holes, these cosmic phenomena represent their own kind of edge, a boundary called the event horizon, beyond which nothing that enters can ever return. The physics of black holes has given scientists crucial insights into how boundaries might work in the cosmos. Stephen Hawking's groundbreaking work on black hole thermodynamics revealed that these boundaries aren't as absolute as once thought. They can emit radiation and eventually evaporate over unimaginably long timescales. Could the universe itself have something analogous to an event horizon? In a sense, it does. The cosmic horizon marks the boundary of our observable universe. But unlike a black hole's event horizon, this boundary isn't fixed. It recedes as the universe ages, revealing more and more of the cosmos. At least, that's what would happen if the universe weren't expanding. The expansion of the universe is one of the most profound discoveries in modern astronomy. Edwin Hubble first observed that distant galaxies are moving away from us, and the farther they are, the faster they seem to be receding. This observation led to the realization that space itself is stretching, carrying galaxies along like raisins in an expanding loaf of bread. This expansion has dramatic consequences for our ability to observe the cosmos. Light from extremely distant objects has to travel through space that is itself expanding, which means that some regions of the universe are receding from us faster than the speed of light due to this cosmic expansion. Light from those regions will never reach us, no matter how long we wait. This creates a fundamental limit to what we can observe, a cosmic horizon beyond which the universe is forever hidden from view. It's estimated that the observable universe is about 93 billion light-years in diameter, a number that seems to contradict the universe's age of roughly 14 billion years. The discrepancy comes from cosmic expansion. The space between us and distant objects has been stretching during the entire time their light has been traveling toward us. The idea that parts of the universe might be permanently unobservable leads to fascinating philosophical questions. Can we meaningfully talk about the existence of things we can never, even in principle, observe? This brings to mind the old philosophical puzzle. If a tree falls in a forest and no one is around to hear it, does it make a sound? In the cosmic version, if a galaxy exists beyond our observable universe, with no possibility of its light ever reaching us, in what sense does it exist for us? These questions become even more complex when we consider theories like cosmic inflation. According to inflation theory, the very early universe underwent a period of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang. This rapid inflation would have stretched space so quickly that regions that were once close enough to interact would have been pulled far apart, potentially beyond each other's observable horizons. Inflation theory leads to mind-boggling implications. It suggests that our observable universe might be just a tiny patch in an inconceivably vast cosmos. Some versions of the theory predict that inflation never completely stops, creating an eternally inflating multiverse where new bubble universes constantly form, each with potentially different physical laws and constants. The multiverse concept represents perhaps the ultimate frontier in our exploration of what lies beyond the edge of the universe. Could our entire universe, with its billions of galaxies and trillions of stars, be just one universe among countless others in a vast multiverse? This idea has moved from the realm of science fiction into serious theoretical physics. Though direct evidence remains elusive, one of the most intriguing versions of multiverse theory comes from quantum mechanics, the branch of physics that governs the behavior of matter and energy at the smallest scales. According to some interpretations of quantum mechanics, every possible outcome of every quantum event actually occurs, splitting reality into countless parallel universes. In this many worlds interpretation, there could be versions of you living entirely different lives, in universes that branched off from our own with every quantum decision. While such ideas might seem to border on science fiction, they arise from our most successful physical theories, pushed to their logical conclusions. String theory, a candidate for the unified theory of physics that Einstein sought throughout the latter part of his life, suggests that our universe might be one of many existing in higher dimensional space, like sheets hanging in a cosmic laundry room. The concept of higher dimensions is itself challenging to visualize. We're familiar with three spatial dimensions: up, down, left, right, forward/backward, plus time as a fourth dimension. But mathematics allows for the possibility of additional spatial dimensions. These extra dimensions might be curled up so tightly that they're effectively invisible to us, manifesting only in the fundamental forces of nature. In fact, the mysterious dark energy that drives the accelerating expansion of the universe might be related to these higher dimensions. Some theories propose that dark energy could be leaking from higher dimensions into our three-dimensional space, causing it to expand at an accelerating rate. Dark energy remains one of the biggest mysteries in modern cosmology. Discovered in 1998 through observations of distant supernovae, dark energy appears to make up about 68% of the total energy content of the observable universe. Yet we know remarkably little about what it actually is. Equally mysterious is dark matter, which makes up about 27% of the universe. Unlike dark energy, which is spread evenly throughout space, dark matter clumps together gravitationally. We can detect its gravitational effects on visible matter, but it doesn't interact with light, making it invisible to our telescopes. Together, dark energy and dark matter account for about 95% of the universe's total energy content. This means that all the stars, planets, galaxies, and everything else we can directly observe make up just 5% of what's out there. We are, in a very real sense, just seeing the tip of the cosmic iceberg. This realization is humbling. It reminds us that despite all our technological advances and scientific knowledge, we're still just beginning to understand the true nature of the cosmos. The edge of the universe isn't just a physical boundary, it's the frontier of human knowledge. As we peer out to this cosmic horizon with our most powerful telescopes, we're essentially looking back in time. The light from the most distant galaxies we can observe has been traveling toward us for almost the entire history of the universe. This gives us a unique window into the universe's past, allowing us to study how galaxies formed and evolved over cosmic time. But there's a limit to how far back we can see using light. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. Before this recombination event, the universe was an opaque plasma that scattered light rather than transmitting it. The oldest light we can detect directly is the cosmic microwave background radiation, the afterglow of the Big Bang itself, which gives us a picture of the universe at this 380,000-year mark. To probe earlier times, scientists must rely on other cosmic messengers, such as neutrinos and gravitational waves, which can pass through the opaque early universe. Gravitational wave observatories have already detected ripples in space-time from colliding black holes and neutron stars, opening a new window on the cosmos. Future detectors might even be able to detect gravitational waves from the Big Bang itself, giving us unprecedented insights into the birth of the universe. The study of the very early universe brings us to the fascinating intersection of cosmology and particle physics. The conditions in the first fraction of a second after the Big Bang were so extreme that understanding them requires both Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. Unfortunately, these two pillars of modern physics are fundamentally incompatible in their current forms. Developing a theory of quantum gravity that reconciles them is one of the greatest challenges in theoretical physics today. Such a theory might reveal new insights about the universe's beginning and potentially what lies beyond its edge. Some approaches to quantum gravity, like loop quantum cosmology, suggest that the Big Bang wasn't actually the beginning of everything, but rather a big bounce, a transition from a previous contracting phase of the universe to our current expanding phase. If true, this would mean that what we think of as the beginning of time might just be one chapter in a much longer cosmic story. Other theories propose that our universe might have emerged from the quantum vacuum, a state that, despite its name, isn't completely empty, but rather seethes with quantum fluctuations, where pairs of particles and antiparticles briefly pop into existence before annihilating each other. Under the right conditions, such fluctuations might have given birth to our entire universe. The idea that universes can be born from quantum fluctuations ties back to the multiverse concept. If it happened once for our universe, it could happen countless times, creating a vast ensemble of universes with different properties. This brings us to another profound question. Why does our universe have the specific physical laws and constants that it does? The fundamental constants of nature, such as the strength of gravity, the mass of the electron, and the speed of light, seem finely tuned to allow for the existence of stars, planets, and ultimately life. If these constants were even slightly different, the universe would be a very different place, potentially without the complexity needed for life to emerge. Some scientists see this apparent fine-tuning as evidence for a multiverse, combined with a selection effect known as the anthropic principle. In a multiverse with varying physical laws, we naturally find ourselves in a universe compatible with our existence. Other universes might exist with different physical laws, but they wouldn't contain observers to wonder about them. Others see the fine-tuning as potential evidence for design, though this interpretation moves beyond the realm of science into philosophy and theology. Science can tell us what the universe is like and how it works, but questions of why it exists or whether it has a purpose venture into territory where scientific methods may not apply. As we grapple with these profound questions about the nature of reality, it's worth remembering that throughout history, our conception of the universe has repeatedly expanded. Ancient civilizations saw Earth as the center of a relatively small cosmos, The Copernican revolution placed the Sun at the center instead. Later, we realized our Sun is just one of hundreds of billions of stars in the Milky Way galaxy, which itself is one of hundreds of billions of galaxies in the observable universe. Now we face the possibility that even this vast observable universe might be just a tiny part of a much larger, perhaps infinite, cosmos. Each expansion of our cosmic perspective has required us to rethink our place in the universe. We've moved from seeing ourselves at the center of creation to recognizing that we occupy a tiny, seemingly unremarkable corner of an incomprehensibly vast cosmos. Yet there's something remarkable in the fact that, despite our physical insignificance on the cosmic scale, we've been able to comprehend so much about the universe. The same laws of physics that govern the behavior of atoms in our bodies also govern the evolution of galaxies billions of light years away. The carbon in our cells was forged in the hearts of ancient stars that exploded long before our solar system formed. In a very real sense, we are the universe becoming conscious of itself. This perspective gives a profound meaning to our quest to understand what lies beyond the edge of the universe. It's not just an abstract scientific pursuit. It's part of the universe's own journey towards self-knowledge. As we continue our exploration of the cosmos, we'll delve deeper into what modern science tells us about the structure of the universe, its history, and its possible future. We'll examine the evidence for different theories about what might lie beyond what we can observe, and we'll consider how future discoveries might reshape our understanding. The edge of the universe represents the boundary not just of what we can see, but of what we currently understand. Like explorers throughout human history, we're drawn to this frontier by an insatiable curiosity about what lies beyond. And like those explorers, we find that each new discovery doesn't just answer old questions, it raises new ones, leading us ever deeper into the mystery of existence. To truly understand what might lie beyond the edge of the universe, we first need a clear picture of what the universe actually is. The word universe comes from the Latin universum, meaning turned into one, or combined into one whole. But what exactly is this whole that we call the universe? At its most basic definition, the universe is everything that exists, all matter, energy, space, and time. But this seemingly simple definition contains extraordinary complexity when we examine it more closely. Let's start with what we can directly observe. When you look up at the night sky from a dark location, away from city lights, you can see thousands of stars with your naked eye. These stars are just a tiny fraction of the roughly 100 billion stars in our home galaxy, the Milky Way. The Milky Way itself is a vast spiral galaxy, spanning approximately 100,000 light-years from edge to edge. A light year, the distance light travels in 1 year, equals about 9.5 trillion kilometers. So our galaxy alone spans about 950,000 trillion kilometers, a distance so vast that the human mind struggles to comprehend it. Yet astonishingly, the Milky Way is just one galaxy among trillions in the observable universe. Galaxies come in various shapes and sizes. Spiral galaxies like our Milky Way, elliptical galaxies that look like cosmic footballs, and irregular galaxies with no definite shape. These galaxies aren't distributed randomly throughout space. They form an intricate cosmic web, with galaxies clustered together in groups and clusters, which themselves form even larger structures called superclusters. The Milky Way, for instance, is part of the Local Group, a collection of more than 50 galaxies dominated by the Milky Way and the Andromeda Galaxy. The Local Group, in turn, is part of the Virgo supercluster, which contains at least 100 galaxy groups and clusters. And the Virgo supercluster is just one component of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies. These enormous structures, galaxies, clusters, and superclusters, make up the visible matter in our universe. But remarkably, this visible matter constitutes only about 5% of the universe's total content. The rest consists of two mysterious components, dark matter and dark energy. Dark matter, making up about 27% of the universe, doesn't interact with light or other forms of electromagnetic radiation, making it invisible to our telescopes. We know it exists because of its gravitational effects on visible matter. Without dark matter, galaxies would fly apart. They simply don't have enough visible mass to hold themselves together through gravity alone. Dark matter forms a kind of invisible scaffold around galaxies, holding them together and influencing their formation and evolution. Even more mysterious is dark energy, which accounts for about 68% of the universe's content. Unlike dark matter, which clumps together like visible matter, dark energy appears to be distributed uniformly throughout space. Its most notable effect is driving the accelerating expansion of the universe. For reasons we don't yet fully understand, the expansion of the universe isn't slowing down due to gravity as one might expect. It's speeding up, as if some invisible force is pushing everything apart. Together, visible matter, and dark energy make up the known content of our universe. But there's another crucial aspect to understanding the universe: its structure in both space and time. When we talk about the universe, we're not just referring to a collection of objects in space. According to Einstein's theory of general relativity, space and time are woven together into a four-dimensional fabric called space-time. This fabric isn't fixed and rigid. It can be warped and curved by the presence of mass and energy. This warping of space-time manifests as what we experience as gravity. Massive objects like stars and planets create dents in this cosmic fabric, causing other objects to follow curved paths around them, what we observe as orbits. Black holes, the most extreme objects in the universe, create such deep depressions in space-time that nothing, not even light, can escape once it passes a certain boundary called the event horizon. The concept of space-time being warped by mass and energy is crucial for understanding the large-scale structure of the universe. On a cosmic scale, the distribution of matter and energy throughout the universe determines its overall geometry. Depending on the average density of matter and energy, the universe could have one of three possible geometries: flat, closed, or open. In a flat universe, parallel lines remain parallel forever, and the sum of angles in a triangle equals 180 degrees. Just like in the Euclidean geometry we learned in school, in a closed universe, which has positive curvature like the surface of a sphere, parallel lines eventually intersect, and the sum of angles in a triangle exceeds 180 degrees. In an open universe, with negative curvature like a saddle, parallel lines diverge, and triangles contain less than 180 degrees. Current observations strongly suggest that our universe is flat, or very nearly so. This flatness is actually a cosmic puzzle because it requires an extraordinarily precise balance between the universe's expansion rate and its density. Without some mechanism to explain this precision, it seems like an incredible coincidence. One chance in a trillion. This problem, known as the flatness problem, is one of several puzzles that led to the development of cosmic inflation theory. Cosmic inflation proposes that the very early universe, just a fraction of a second after the Big Bang, underwent a period of extraordinarily rapid expansion. During this brief moment, the universe expanded faster than the speed of light, doubling in size many times over in less than a billionth of a second. This rapid expansion would have stretched space so dramatically that any initial curvature would have been flattened out, just as the surface of a balloon appears flatter and flatter as you inflate it to enormous size. Inflation not only explains the flatness of the universe, but also solves several other cosmological puzzles. It explains why the universe appears so uniform on large scales. Different regions that could never have been in contact with each other somehow have the same temperature and density. Inflation suggests that these regions were actually in contact before inflation drove them apart. The inflationary period was incredibly brief, but its effects on the structure of the universe were profound and permanent. After inflation ended, the universe continued to expand, but at a much slower rate. The energy that drove inflation was converted into a hot soup of fundamental particles, quarks, electrons, and photons that would eventually form the atoms, stars, and galaxies we see today. This brings us to another crucial aspect of understanding the universe: its history. The universe has a chronology, a sequence of epochs stretching from the Big Bang to the present day and beyond into the future. The Big Bang wasn't an explosion in space, but rather an expansion of space itself. About 13.8 billion years ago, all the matter and energy in the observable universe was compressed into an incredibly hot, dense state. We can't observe the moment of the Big Bang itself. Our theories of physics break down at the extreme conditions that existed then, but we can trace the universe's evolution from a tiny fraction of a second after this moment. After inflation ended, the universe was filled with a hot plasma of fundamental particles. As the universe expanded and cooled, these particles began to combine in new ways. Quarks bound together to form protons and neutrons. About 3 minutes after the Big Bang, these protons and neutrons began to fuse to form the nuclei of the lightest elements, mainly hydrogen and helium, with traces of lithium. For the next 380,000 years, the universe was still too hot for electrons to bind with these nuclei to form complete atoms. Light couldn't travel far in this electronically charged plasma. It would scatter off the free electrons, making the universe opaque like a dense fog. But as the universe continued to expand and cool, it reached a crucial temperature threshold where electrons could bind with nuclei to form neutral atoms. Suddenly, light could travel freely through space. This moment, known as recombination, is crucial for our understanding of the universe because it represents the oldest light we can directly observe. The cosmic microwave background radiation, the afterglow of the Big Bang itself, shows us what the universe looked like at this moment, about 380,000 years after the Big Bang. This ancient light has been stretched by the expansion of the universe from visible light to microwave radiation, but it still carries valuable information about the early universe. After recombination, the universe entered a period often called the Cosmic Dark Ages. The first stars hadn't yet formed, and the universe was filled with neutral hydrogen gas. This period lasted for hundreds of millions of years until the first stars began to shine, bringing light back to the cosmos in what astronomers call the cosmic dawn. These first stars were unlike any that exist today. They formed from primordial hydrogen and helium with virtually no heavier elements. Without these heavier elements to help cool the gas, the clouds that collapsed to form these first stars had to be much more massive than those that form stars today. The resulting stars were giants, perhaps hundreds of times more massive than our Sun, and burned hot and bright, living fast and dying young in spectacular supernova explosions. These supernovae scattered the first heavy elements, carbon, oxygen, silicon, iron, throughout the cosmos. These elements, forged in the hearts of the first stars, would become the building blocks for planets, for complex chemistry, and eventually for life itself. In a very real sense, we are made of stardust. The atoms in our bodies were created in ancient stars that exploded billions of years ago. Over time, more and more stars formed. Galaxies began to take shape, and the large-scale structure of the universe, the cosmic web of galaxies, clusters, and superclusters, emerged. About 4.5 billion years ago, in a spiral arm of the Milky Way galaxy, a cloud of gas and dust collapsed to form our Sun and its planets, including Earth. And here we are, on this tiny blue planet, looking out at the vast cosmos and trying to understand our place within it. We've come to realize that the observable universe, the part we can potentially see, is likely just a fraction of what exists. The observable universe is limited by the finite speed of light and the finite age of the universe. We can only see objects whose light has had enough time to reach us since the beginning of the universe. Given the age of the universe, about 13.8 billion years, you might think that the most distant objects we could possibly see would be 13.8 billion light years away. But the actual size of the observable universe is much larger, roughly 93 billion light years in diameter. This apparent contradiction arises because space itself has been expanding while the light from distant objects has been traveling toward us. It's as if the light has been swimming upstream against a current that's getting stronger with distance. Beyond this cosmic horizon lies the unobservable universe, regions of space whose light hasn't had time to reach us yet, and in many cases, never will. This brings us to a crucial distinction: the difference between the observable universe and the entire universe. The observable universe refers to the spherical region centered on Earth, encompassing everything we can potentially observe. The entire universe, on the other hand, includes everything that exists, whether we can observe it or not. The entire universe might be finite or infinite in size. Our observations can't tell us which, because we can only see a finite portion of it. If the universe is finite, it could still be boundless, without an edge, just as the surface of the Earth is finite, but has no edge. You can travel around the Earth indefinitely without ever reaching an edge. Similarly, a finite universe might wrap around on itself in higher dimensions, allowing hypothetical travelers to return to their starting point if they traveled far enough in one direction. If the universe is infinite, then it extends forever in all directions, containing an infinite number of galaxies, stars, and potentially even an infinite number of exact copies of Earth and everyone on it. A mind-boggling consequence of the fact that in an infinite universe with a finite number of possible particle configurations, those configurations must eventually repeat. Whether finite or infinite, the entire universe is likely vastly larger than the part we can observe. Some estimates based on inflation theory suggest that the entire universe might be at least 10 to the power of 23 times larger than the observable universe. That's a 1 followed by 23 zeros. And some versions of inflation theory suggest the universe might be infinite. This vast scale challenges our intuition and stretches the limits of our comprehension. How can we make sense of something so enormous? How can we understand what might lie beyond the edge of what we can see? One approach is to look for patterns and regularities within the observable universe that might give us clues about its larger structure. The universe appears remarkably uniform on the largest scales. The distribution of galaxies and the properties of the cosmic microwave background are nearly identical in all directions. This uniformity, known as the cosmic principle of homogeneity and isotropy, suggests that the universe has no special direction or location, no center and no edge. Another approach is to develop mathematical models based on our current understanding of physics and cosmology, and then extrapolate these models beyond what we can directly observe. This is the essence of theoretical cosmology, using the laws of physics as we understand them to predict what might exist beyond our cosmic horizon. These theoretical models have led to some extraordinary ideas, including the possibility that our universe might be just one of many in a vast multiverse. But before we explore these more speculative ideas, it's worth reflecting on the remarkable fact that we can understand as much as we do about the universe. Humans have evolved on a tiny planet, adapted to perceive the world at scales relevant to our survival, from millimeters to kilometers, from seconds to years. Yet somehow, we've developed the intellectual and technological tools to comprehend scales from subatomic particles to the cosmic web of galaxies, from the fleeting lifetimes of exotic particles to the 13.8 billion year history of the universe itself. This capacity for understanding, this ability to transcend the limitations of our direct experience, is one of the most remarkable features of human consciousness. Through mathematics, physics, astronomy, and cosmology, we've pieced together a picture of the cosmos that extends far beyond what any individual human can directly perceive. This picture is still incomplete, of course. We don't yet know what dark matter is made of, or what dark energy actually is. We don't know whether the universe is finite or infinite. We don't know what caused the Big Bang, or whether anything existed before it. And we don't know for certain what lies beyond the edge of the observable universe. But the progress we've made in understanding the cosmos, especially over the past century, is truly extraordinary. From Einstein's theories of relativity to the discovery of the cosmic microwave background, from the first observations of distant galaxies to the detection of gravitational waves, we've continually expanded the boundaries of our cosmic knowledge. As we continue our journey exploring the edge of the universe, we'll examine the limits of what we can observe, the theories that might tell us what lies beyond, and the future of our cosmic exploration. The universe is not just a subject of scientific study, it's our home, our context, the vast and ancient reality from which we emerged and to which we belong. Understanding the universe is, in a very real sense, understanding ourselves. With this foundation in place, understanding what the universe is, how it's structured, and how it has evolved over time, we can now turn to the question of its observable limits. How far can we see into the cosmos, and what determines the boundary of our cosmic perspective? This brings us to the concept of the observable universe and the cosmic horizon, the subject of our next exploration. Now that we understand what the universe is, let's explore the limits of what we can actually see. How far can we peer into the cosmic darkness, and what determines the boundary of our vision? When you gaze up at the night sky, you're not just looking across vast distances, you're looking back in time. Light, though incredibly fast at 300,000 kilometers per second, still takes time to travel from distant objects to our eyes. The light from the moon takes about 1.3 seconds to reach us, meaning we see the moon as it was 1.3 seconds in the past. Sunlight takes roughly 8 minutes and 20 seconds to reach Earth, so we see the sun as it was more than 8 minutes ago. These delays are negligible for objects within our solar system, but they become profound when we look at more distant objects. The nearest star to our solar system, Proxima Centauri, is about 4.2 light years away. This means the light we see from it today began its journey more than 4 years ago. The beautiful Andromeda Galaxy, visible to the naked eye on dark nights, is approximately 2.5 million light years away. We see it as it was when early human ancestors were just beginning to use stone tools on Earth. The most distant objects we can observe are billions of light years away. The light from these objects has been traveling through space for the majority of the universe's existence. When we look at a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago, less than 4 billion years after the Big Bang. This connection between distance and time creates what astronomers call the cosmic horizon or the particle horizon. This horizon represents the maximum distance from which light could have reached us since the beginning of the universe. Given that the universe is about 13.8 billion years old, you might think this horizon would be 13.8 billion light years away. But the actual situation is more complex. The universe has been expanding throughout the time that light has been traveling toward us. This means the most distant objects we can see today are much farther away than 13.8 billion light years. They're now about 46.5 billion light years away in any direction, making the diameter of the observable universe about 93 billion light years. This seemingly paradoxical situation arises because these distant objects weren't always so far away. When they emitted the light we're now receiving, they were much closer to us. As the light traveled across space, the universe continued to expand, increasing the distance between us and these objects. It's a bit like swimming across a river that's getting wider as you swim. You might reach the other side, but it will be much farther downstream than where you aimed. The cosmic horizon isn't a physical boundary, but rather a limit to our observational capabilities. Beyond this horizon lie regions of space whose light simply hasn't had enough time to reach us since the beginning of the universe. We cannot see these regions, no matter how powerful our telescopes, because their light hasn't arrived yet. Some light from regions just beyond our current cosmic horizon will reach us in the future, gradually expanding our observable universe. However, due to the accelerating expansion of the universe, there are regions of space whose light will never reach us, even if we waited an infinite amount of time. These regions are forever beyond our cosmic horizon, separated from us by the relentless expansion of space itself. To understand this accelerating expansion and its effects on what we can observe, we need to examine how astronomers discovered it and what's driving it. In the late 1920s, astronomer Edwin Hubble made a groundbreaking discovery. By measuring the distances to galaxies and the apparent shift in their light toward the red end of the spectrum, known as redshift, he found a direct relationship. The farther away a galaxy is, the faster it appears to be moving away from us. This observation, now known as Hubble's law, provided the first empirical evidence that the universe is expanding. For most of the 20th century, astronomers assumed this expansion was slowing down due to the gravitational attraction between galaxies and clusters. It seemed logical. Gravity should gradually break the expansion, like an object thrown upwards slows as Earth's gravity pulls it back. But in 1998, two independent research teams studying distant supernovae made a shocking discovery. These stellar explosions appeared dimmer than expected, indicating they were farther away than they should have been if the universe's expansion was slowing down. The inescapable conclusion was that the expansion of the universe isn't slowing down, it's speeding up. This accelerating expansion has profound implications for what we can observe. Regions of space that are currently beyond our cosmic horizon and receding from us faster than the speed of light will never become visible to us. Their light, traveling through ever-expanding space, will never reach our location. Conversely, galaxies that we can see today will eventually disappear from view as the accelerating expansion carries them beyond our cosmic horizon. You might wonder how galaxies can recede faster than the speed of light, given that Einstein's theory of relativity states that nothing can travel faster than light. The key distinction is that these galaxies aren't moving through space faster than light. Rather, the space between us and them is expanding. This expansion of space itself isn't limited by the speed of light. It's not the galaxies breaking Einstein's cosmic speed limit. It's the fabric of space itself, stretching between them. This concept of the expanding universe helps us understand another crucial boundary to our observations, the cosmic microwave background radiation, or CMB. The CMB is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before this recombination event, the universe was an opaque plasma. Light couldn't travel far without scattering off free electrons, much like light struggles to penetrate a dense fog. After recombination, the universe became transparent, allowing light to travel freely through space. The CMB represents this moment of transition. It's the point beyond which we cannot see using electromagnetic radiation like light. When we observe the CMB, we're looking at a sphere surrounding us in all directions, about 46.5 billion light-years away. It marks the edge of the observable universe, not a physical edge, but the limit of what we can see with telescopes that detect light, radio waves, X-rays, or any other form of electromagnetic radiation. The CMB essentially acts as a wall around our observable universe, blocking our view of anything that happened before recombination. The CMB was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were trying to identify sources of noise in a communications antenna. What they found was a faint microwave signal coming equally from all directions in space, the afterglow of the Big Bang itself. This discovery provided compelling evidence for the Big Bang theory and earned Penzias and Wilson the Nobel Prize in Physics. Since its discovery, the CMB has been studied in extraordinary detail by satellites including NASA's Cosmic Background Explorer (COBE), the Wilkinson Microwave Anisotropy Probe (WMAP), and the European Space Agency's Planck mission. These observations have revealed tiny temperature fluctuations in the CMB, differences of just 1 part in 100,000, that represent the seeds from which all the structure in our universe grew. These fluctuations are like cosmic fossils, preserving information about the very early universe. By studying their patterns, scientists have determined that the universe is flat, or very nearly so, that it's composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. and that it's about 13.8 billion years old. The CMB has become one of our most valuable tools for understanding the early universe and its evolution. While the CMB represents the limit of what we can see using light, it's not necessarily the absolute limit of what we can observe. Other cosmic messengers, like neutrinos and gravitational waves, can potentially carry information from before the CMB was formed. Neutrinos are nearly massless particles that interact very weakly with matter, allowing them to travel virtually unimpeded through the universe. In principle, we could detect cosmic neutrino background radiation from about 1 second after the Big Bang, when the universe cooled enough for neutrinos to stop interacting frequently with other particles. This would push our observational horizon much closer to the beginning of the universe, though detecting this neutrino background remains beyond our current technological capabilities. Gravitational waves, ripples in the fabric of space-time created by accelerating massive objects, offer another window into the early universe. Unlike light, gravitational waves can pass through the opaque plasma that existed before recombination. Future gravitational wave observatories might be able to detect signals from the inflationary period, just a tiny fraction of a second after the Big Bang, potentially revealing information about the universe at its earliest moments. So far, we've discussed the cosmic horizon as a sphere centered on Earth, which might suggest that we occupy a special place in the universe. But this isn't the case. The observable universe is centered on the observer. Any observer, anywhere in the universe, will find themselves at the center of their own observable universe. An alien in a galaxy billions of light years away would have a different cosmic horizon, would see different galaxies, and would define the observable universe differently than we do. This concept relates to the cosmological principle, which states that the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, on large scales. There are no special locations or directions in the universe. Every observer, no matter where they are, will see roughly the same universe when they look out to their cosmic horizon. The implications of this principle are profound. It means that beyond our cosmic horizon, the universe likely continues with the same general properties. Stars, galaxies, clusters, and superclusters distributed according to the same patterns we observe within our horizon. There's no reason to suspect that the fundamental laws of physics change beyond what we can see, or that the universe suddenly ends at our horizon. This brings us to a crucial distinction: the difference between the observable universe and the entire universe. The observable universe is the spherical region centered on Earth, encompassing everything we can potentially observe, given the finite age of the universe and the finite speed of light. The entire universe, on the other hand, includes everything that exists, whether we can observe it or not. How big is the entire universe? We don't know. It might be finite, but unbounded, like the surface of a sphere. It might be infinite, extending forever in all directions. Our observations can't tell us which is correct, because we can only see a finite portion of the universe. Some theoretical models, particularly those based on cosmic inflation, suggest that the entire universe might be at least 10 to the power of 23 times larger than the observable universe, or even infinite. What makes this question particularly challenging is that we can never observe the entire universe if it's larger than our cosmic horizon. We're fundamentally limited by the speed of light and the age of the universe. It's a bit like trying to determine the size of an ocean while confined to a small island in the middle of it. You can look to the horizon in all directions, but what lies beyond remains inaccessible to direct observation. Despite these limitations, astronomers have developed ingenious methods to push the boundaries of what we can observe and to extract maximum information from the light that reaches us. The Hubble Space Telescope, launched in 1990, revolutionized our view of the distant universe by placing a powerful telescope above Earth's atmosphere, which blurs and blocks much of the light from space. Hubble's successor, the James Webb Space Telescope, launched in December 2021, is designed to observe in infrared wavelengths, allowing it to see even farther back in time. Because the expansion of the universe stretches light waves, making them longer and redder, the most distant galaxies are only visible in infrared light. Webb can potentially observe galaxies as they were just a few 100 million years after the Big Bang, when the first stars and galaxies were forming. Ground-based observatories are also pushing the boundaries of what we can see. Enormous telescopes with mirrors spanning tens of meters, equipped with adaptive optics to counteract atmospheric turbulence, can collect unprecedented amounts of light from distant sources. Radio telescope arrays, spanning continents, or even using satellites can achieve extraordinary resolution, revealing details that would otherwise remain hidden. These technological advances allow us to observe objects that are fainter, more distant, and from earlier in the universe's history than ever before. Yet they all share a fundamental limitation. They can only detect signals that have reached Earth. No matter how powerful our telescopes become, they cannot see beyond our cosmic horizon. This limitation shapes how we think about the edge of the observable universe. It's not a physical boundary in space, but rather a boundary in our knowledge, a horizon beyond which we cannot see with our current vantage point in space and time. This horizon isn't fixed. It recedes slightly each year as light from previously unobservable regions reaches us. But due to the accelerating expansion of the universe, this recession will eventually stop, and the observable universe will reach a maximum size. As we peer toward this horizon, we're looking back to the earliest moments of cosmic history. The most distant galaxies we can observe appear to us as they were billions of years ago, when the universe was just a fraction of its current age. These observations reveal a universe very different from the one surrounding us today, a universe that was hotter, denser, and more chaotic, with galaxies that were smaller, more irregular, and forming stars at a much higher rate than modern galaxies. By studying these distant objects, astronomers can trace the evolution of the universe over cosmic time. They can see how galaxies formed and evolved, how the elements necessary for life were created in stellar furnaces and scattered by supernovae, and how the vast cosmic web of filaments and voids emerged from tiny quantum fluctuations in the early universe. This cosmic archaeology, piecing together the history of the universe from the light that reaches us, is one of the most remarkable achievements of modern astronomy. It allows us to understand not just what the universe looks like today, but how it came to be the way it is. A story that stretches back nearly 14 billion years to the earliest moments after the Big Bang. But the cosmic horizon limits how far back we can trace this history using light. The CMB represents the earliest electromagnetic radiation we can detect, showing us the universe as it was about 380,000 years after the Big Bang. What happened before that remains largely invisible to us, accessible only through theoretical models and perhaps future observations of gravitational waves or neutrinos. This limitation has profound implications for our understanding of the universe's beginnings. We can't directly observe the Big Bang itself or the inflationary period that followed. The conditions during these earliest moments were so extreme that our current theories of physics may not adequately describe them. Understanding what happened in the first tiny fraction of a second after the Big Bang requires a theory of quantum gravity, a unified description of gravity and quantum mechanics, which we haven't yet fully developed. The cosmic horizon thus represents not just the limit of what we can see, but in some ways the limit of what we can know with certainty about the universe's history. Beyond this horizon lies the realm of theoretical inference and mathematical models, regions of space and time that remain inaccessible to direct observation. Yet this shouldn't be seen as a cause for despair, but rather as an invitation to wonder and exploration. Throughout history, humans have faced horizons that seemed impassable: the edge of the known world, the depths of the oceans, the boundary of Earth's atmosphere. In each case, human ingenuity, curiosity, and determination have found ways to push beyond these horizons, revealing new wonders and expanding our understanding of the world. The cosmic horizon presents a different kind of challenge, one imposed by the fundamental laws of physics rather than by the limitations of our technology. We can't travel faster than light or create a telescope that can see beyond our cosmic horizon. But we can continue to develop more powerful instruments to observe what lies within our horizon with greater clarity and detail. We can create more sophisticated mathematical models to infer what might lie beyond. And we can search for new cosmic messengers, particles or waves that might carry information from regions we can't observe with light. The observable universe, with its estimated 2 trillion galaxies, each containing billions of stars, represents an almost unimaginably vast realm for exploration. Even with our most powerful telescopes, we've barely begun to catalogue and understand the objects within our cosmic horizon. There are countless discoveries waiting to be made, mysteries to be solved, and wonders to be revealed within the boundaries of what we can observe. And perhaps, as we continue to explore and understand the observable universe, we'll gain new insights into what might lie beyond, the unobservable universe that extends past our cosmic horizon. This brings us to our next question. What do scientists think exists in the unobservable universe, beyond the limits of what we can see? As we ponder this question, it's worth reflecting on the remarkable fact that we can even ask it. From our tiny planet, orbiting an ordinary star in one galaxy among trillions, we've managed to map the observable universe, understand its basic composition and structure, and trace its history back nearly to the beginning of time. This cosmic perspective, seeing ourselves as part of a vast, ancient, and evolving universe, is one of the greatest intellectual achievements of our species. The observable universe, with its cosmic horizon determined by the speed of light and the age of the universe, represents the limit of what we can directly see. But it doesn't limit our curiosity or our capacity to wonder about what lies beyond. As we turn our attention to the unobservable universe in our next exploration, we'll venture into a realm where science and imagination meet, where the constraints of direct observation give way to the power of theoretical inference and mathematical modeling. The cosmic horizon marks not the end of our journey, but rather a threshold, a boundary between what we can observe and what we can only imagine or infer. Beyond this horizon lies a cosmic landscape that, while forever hidden from direct view, still captures our imagination and drives our quest to understand the ultimate nature of reality. We've explored the observable universe, that vast yet finite sphere centered on Earth, extending about 46.5 billion light-years in all directions. But what lies beyond this cosmic horizon? What exists in the regions of space from which light has not yet reached us, and in many cases, never will? This is where we leave the realm of direct observation and enter a landscape shaped by theoretical inference, mathematical modeling, and carefully reasoned speculation. While we cannot see beyond our cosmic horizon, we can use our understanding of physics and cosmology to make educated guesses about what might exist there. The simplest and most widely accepted idea is that the unobservable universe is essentially more of the same. More galaxies, more clusters, more filaments, and voids forming the cosmic web, all following the same physical laws we observe within our horizon. This idea, known as the cosmological principle, suggests that the universe is homogeneous and isotropic on large scales. It looks roughly the same no matter where you are or which direction you look. The cosmological principle has strong empirical support within the observable universe. When astronomers look in different directions at equal distances from Earth, they see a remarkably similar universe. The distribution of galaxies, the properties of the cosmic microwave background radiation, and the large-scale structure of the cosmic web all exhibit a high degree of uniformity. This uniformity becomes most apparent when we look at scales larger than about 300 million light-years, where the statistical properties of the universe become essentially the same everywhere. If this principle holds beyond our cosmic horizon, and there's no compelling reason to think it doesn't, then the unobservable universe would contain more galaxies similar to those we can see, arranged in similar patterns of clusters, filaments, and voids. The laws of physics would be the same, and the fundamental constants of nature, like the speed of light, the strength of gravity, and the properties of elementary particles would have the same values. But how far does this unobservable universe extend? Is it finite or infinite? Here, scientists remain uncertain, though theoretical models provide some intriguing possibilities. Some models suggest that the entire universe is far larger than the part we can observe, perhaps by many orders of magnitude. Theories based on cosmic inflation, which proposes that the very early universe underwent a period of extraordinarily rapid expansion, suggest that the entire universe might be at least 10 to the power of 23 times larger than the observable universe. That's a 1 followed by 23 zeros, a scale so vast it defies comprehension. In such an enormous universe, the part we can observe would be just a tiny fraction of the whole, like a single grain of sand on all the beaches of the Earth. Our cosmic horizon would enclose just one patch of a much vaster cosmos, with countless other regions that remain forever beyond our view. Other theoretical models go even further, suggesting that the universe might be infinite, extending forever in all directions, without any boundary or edge. An infinite universe would contain an infinite number of galaxies, stars, and planets. It would even contain an infinite number of regions exactly like our observable universe, including perfect copies of the Milky Way galaxy, the solar system, Earth, and every person on it. In fact, in an infinite universe with a finite number of possible ways to arrange particles, every possible configuration must repeat infinitely many times. This mind-boggling consequence of infinity, what cosmologists sometimes call the cosmic doppelganger scenario, follows from simple probability. If you have an infinite universe and a finite number of ways to arrange particles within a given volume, which quantum physics suggests is the case, then any particular arrangement, including the exact arrangement of particles that makes up you and your surroundings, must occur infinitely many times. In such a scenario, there would be infinitely many Earths, infinitely many copies of each person, all with the same history up to a point, after which their experiences would diverge. Some copies would be relatively nearby, though still far beyond our cosmic horizon, while others would be unimaginably distant. These ideas might seem like science fiction, but they emerge naturally from our current understanding of physics and cosmology pushed to its logical conclusions. They're not proven, of course. We have no direct evidence for regions beyond our cosmic horizon, much less for cosmic doppelgangers, but they represent plausible extensions of what we observe within our horizon. Another fascinating possibility is that regions of the universe far beyond our cosmic horizon might have different properties than our observable universe. This idea emerges from certain versions of inflation theory, particularly eternal inflation, which suggests that inflation never completely stops but continues in some regions of space while ending in others. According to eternal inflation, our observable universe is just one bubble in a vast, eternally inflating multiverse. Within this multiverse, bubble universes constantly form, expand, and potentially develop complex structures, including stars, galaxies, and perhaps even life. Each bubble might have different physical laws, different fundamental constants, and consequently, very different properties from our own universe. In some bubble universes, the laws of physics might be only slightly different from ours, perhaps with a slightly stronger force of gravity or a slightly different mass for the electron. Such universes might still form stars and planets, though their properties could differ significantly from those in our universe. Other bubbles might have dramatically different physics, perhaps unable to form atoms or any complex structures at all. This concept of a multiverse with varying physical laws provides an intriguing potential explanation for one of the most puzzling aspects of our universe: its apparent fine-tuning for the existence of life. The fundamental constants of nature in our universe seem exquisitely calibrated to allow for the existence of stable atoms, stars with long lifespans, and the complex chemistry necessary for life. If these constants were even slightly different, the universe would be radically different, likely unable to support life as we know it. This fine-tuning has led some to see evidence of design in the universe. But the multiverse concept offers an alternative explanation. If there are countless bubble universes with different physical laws, we naturally find ourselves in one that allows for our existence. It's not that the universe was designed for life, but rather that life evolved in a universe where the conditions happen to be right. This idea, known as the anthropic principle, suggests that our observations of the universe are necessarily biased by the fact that we exist to make those observations. We shouldn't be surprised to find ourselves in a universe that allows for our existence, even if such universes are extremely rare in the multiverse. After all, we couldn't exist in one of the many bubbles where the laws of physics don't allow for complex structures. The multiverse concept represents a profound shift in how we think about the cosmos. Rather than a single universe with a single set of physical laws, it suggests a vast landscape of different universes, each with its own characteristics. Our observable universe would be just one region in one bubble in this cosmic archipelago. Of course, the multiverse theory faces a significant challenge. How can we test it? Science traditionally relies on empirical observations and experiments that can be repeated and verified. But if other bubble universes lie beyond our cosmic horizon, we can't directly observe them. We can't travel to them, send signals to them, or receive signals from them. They're causally disconnected from our observable universe. Does this mean the multiverse theory isn't scientific? Not necessarily. While we can't directly observe other bubble universes, we might find indirect evidence for their existence. For example, if our universe collided with another bubble universe in the past, it might have left subtle imprints in the cosmic microwave background radiation, a kind of cosmic bruise marking the point of impact. Several research teams have searched for such imprints, looking for unusual patterns or cold spots in the CMB that might indicate a collision with another bubble. So far, these searches haven't found compelling evidence for bubble collisions, but they demonstrate that the multiverse theory can make testable predictions, even if the evidence is subtle and indirect. Theoretical physicists are also exploring other potential ways to test multiverse theories, including predictions about the distribution of galaxies, the properties of dark energy, and the pattern of primordial gravitational waves that might be detected by future observatories. Beyond the multiverse arising from eternal inflation, other theoretical frameworks suggest additional types of parallel universes. String theory, a candidate for a unified theory of physics that reconciles general relativity with quantum mechanics, proposes that our three-dimensional space might be embedded in a higher dimensional space. This framework has given rise to the brain-world scenario, where our universe is a three-dimensional membrane, or brain, floating in a higher dimensional space along with other brains, other universes that might occasionally interact with ours through gravity. Quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, has also given rise to the many worlds interpretation. According to this view, every possible outcome of every quantum measurement actually occurs in some branch of a constantly splitting reality. Each quantum decision point creates a branching of the universe into multiple paths, creating an infinite number of parallel universes that encompass every possible sequence of events. These various multiverse theories, from eternal inflation to brain worlds to many worlds, represent different approaches to understanding what might exist beyond our cosmic horizon. They're not mutually exclusive. The reality beyond our horizon might incorporate elements of several of these frameworks, or it might involve concepts we haven't yet imagined. What all these theories share is the humbling suggestion that our observable universe, despite its almost incomprehensible vastness, might be just a tiny fraction of a much larger reality. Our cosmic horizon, spanning 93 billion light-years, might enclose just one small region of a cosmos that's vastly larger, perhaps infinite, and potentially far stranger than we can currently comprehend. This possibility profoundly affects how we think about our place in the cosmos. Humans have already undergone several revolutions in our cosmic perspective. We've moved from seeing Earth as the center of a small universe to recognizing it as one planet orbiting an ordinary star, in one galaxy among billions in the observable universe. The multiverse concept represents yet another step in this cosmic demotion, suggesting that even our entire observable universe might be just one bubble in a vast cosmic foam. But rather than seeing this as diminishing our significance, we might view it as an expansion of our cosmic context, an invitation to appreciate the extraordinary richness and diversity of reality. Just as discovering the vastness of the observable universe didn't make Earth less precious or human life less meaningful, recognizing the potential vastness of the multiverse doesn't diminish the wonder of our existence. If anything, it makes it all the more remarkable that in this possibly infinite landscape of universes, we find ourselves in one where the complex chemistry of life could emerge and eventually give rise to beings capable of contemplating the cosmos. This perspective connects to a profound idea. The universe has become conscious of itself through us and other potential intelligent beings. The same atoms forged in ancient stars, carbon, oxygen, nitrogen, and others, now form the complex structures of our brains, allowing the universe to reflect on its own existence. In a very real sense, we are the universe thinking about itself. Even if our observations are limited by our cosmic horizon, our minds can venture beyond it, using mathematics, physics, and cosmology to explore what might exist in the unobservable universe. This capacity for abstract thought, for imagining what we cannot directly perceive, is one of the most remarkable features of human consciousness. It allows us to transcend the limitations of our physical perspective and contemplate realities that lie beyond our direct experience. The unobservable universe might remain forever beyond our visual reach, but it's not beyond the reach of our scientific inquiry and philosophical reflection. By studying the observable universe in ever greater detail, by developing more comprehensive theoretical frameworks, and by designing increasingly sophisticated experiments and observations, we can continue to refine our understanding of what might lie beyond our cosmic horizon. In this quest, we're guided by the remarkable success of our current physical theories. General relativity and quantum mechanics, despite their apparent incompatibility, have proven extraordinarily successful in describing the universe at the largest and smallest scales, respectively. They've made predictions that have been verified with astonishing precision, giving us confidence in their fundamental correctness, even if a unified theory remains elusive. These theories, along with the Standard Model of Particle Physics and the Lambda CDM model of cosmology, which incorporates dark matter and dark energy, form the foundation for our understanding of the universe's structure, composition, and evolution. They allow us to make educated inferences about what might exist beyond our cosmic horizon, even if we can't directly observe it. But we should remain humble about these inferences. Throughout history, our understanding of the cosmos has been repeatedly revised as new observations and theories have emerged. The geocentric model gave way to the heliocentric model. Newtonian physics was subsumed within Einsteinian relativity, and the static universe was replaced by the expanding Big Bang universe. Future discoveries may similarly transform our current understanding, potentially revising our conception of what lies beyond our cosmic horizon. This is the nature of science, a continuously evolving process of observation, theory building, testing, and refinement. It doesn't provide absolute certainty, but rather provisional understanding that grows more comprehensive and accurate over time. Our current theories represent our best understanding based on available evidence, but they're subject to revision as new evidence emerges. With this scientific humility in mind, we can appreciate the current state of our knowledge while remaining open to new possibilities. The unobservable universe beyond our cosmic horizon might contain more of the same galaxies, clusters, and voids we see within our horizon. It might encompass a vast multiverse of bubble universes with different physical laws. It might include parallel realities branching from quantum decisions, or brains floating in higher dimensions. Or it might involve phenomena we haven't yet imagined. Whatever the case, the boundary of our observable universe, our cosmic horizon, isn't the end of reality, but merely the limit of what we can directly see. Reality extends beyond this horizon, whether we can observe it or not. Our minds and our scientific theories allow us to glimpse what might lie in these unseen regions, even if our telescopes cannot. As we contemplate what lies beyond our cosmic horizon, we should appreciate the extraordinary fact that we can even ask these questions. From our tiny planet, we've managed to understand the basic structure and history of the observable universe, and to develop theories that might extend our understanding beyond what we can see. This intellectual journey from our limited human perspective to a cosmic perspective, encompassing the entire observable universe and potentially beyond, is one of the greatest achievements of our species. The exploration of what lies beyond our cosmic horizon isn't just a scientific endeavor, but also a philosophical and existential one. It touches on fundamental questions about the nature of reality, the limits of knowledge, and our place in the cosmos. As we continue this exploration, we expand not just our understanding of the universe, but also our understanding of ourselves and our relationship to the vast cosmos in which we live. But what if the universe isn't just a vast expanse of space containing galaxies and other structures? What if it has a more complex topology, a shape that gives it unexpected properties? This brings us to another fascinating question. Does the universe have a physical edge, a boundary where space simply ends? Let's explore this possibility in our next discussion. When we think about edges, our minds naturally turn to familiar objects in our everyday experience. The edge of a table, the shoreline of an ocean, the boundary between two countries. These edges mark the point where one thing ends and another begins. It's tempting to apply this intuitive concept to the universe itself. Does the universe have a physical edge, a boundary where space simply stops? Is there a cosmic shore beyond which nothing exists? This question has fascinated humanity for millennia. Ancient cultures often envisioned the universe as having a definite boundary. In some myths, the sky was a solid dome with stars attached to it, while in others, the known world was surrounded by an infinite ocean or a great void. These early cosmologies reflected our natural tendency to imagine the universe as a bounded space. But as our understanding of the cosmos has evolved, so too has our conception of its potential boundaries. Modern cosmology offers a more nuanced and often counterintuitive perspective on the question of the universe's edge. First, let's clarify what we mean by the universe. In cosmology, the universe encompasses all of space, time, matter, and energy. It includes not just the observable universe, the region from which light has had time to reach us since the Big Bang, but also any unobservable regions beyond our cosmic horizon. So when we ask whether the universe has an edge, we're asking about the nature of space itself on the largest scales. One of the most important insights from Einstein's theory of general relativity is that space isn't just an empty container in which objects exist. Rather, space is a dynamic entity that can curve, stretch, and warp in response to matter and energy. This understanding fundamentally changes how we think about the universe's potential boundaries. In the context of an expanding universe, the question of an edge becomes particularly complex. We know from observations that the universe is expanding. Galaxies are moving away from each other as the space between them stretches. But this expansion isn't like an explosion from a central point into pre-existing empty space. Instead, the expansion is happening everywhere, with every region of space stretching over time. To understand this concept, cosmologists often use the analogy of a balloon being inflated. Imagine a balloon with dots drawn on its surface, representing galaxies. As the balloon inflates, all the dots move away from each other, not because they're moving across the surface of the balloon, but because the surface itself is expanding. Each dot sees all the other dots moving away from it, just as we observe distant galaxies receding from us in all directions. In this analogy, the surface of the balloon represents two-dimensional space. It's curved into a sphere in a higher third dimension, but the surface itself has no edge. It's finite, but boundless. An ant walking on the surface could travel indefinitely without ever reaching a boundary. Our three-dimensional space might have similar properties. It could be curved in a higher fourth spatial dimension, not to be confused with time as the fourth dimension in space-time, creating a finite but boundless universe. In such a universe, you could travel indefinitely in any direction and eventually return to your starting point without ever encountering an edge. This concept of a finite but boundless universe is difficult to visualize because we're accustomed to thinking in terms of objects embedded in space rather than the properties of space itself. But mathematics provides tools to describe such geometries, even if they defy our everyday intuition. Current observations suggest that the universe is flat or very nearly so on large scales. In a flat universe, parallel lines remain parallel forever, and the sum of angles in a triangle equals 180 degrees. Just like in the Euclidean geometry we learned in school, this flatness is consistent with cosmic inflation, which would have stretched the universe so dramatically in its earliest moments that any initial curvature would have been flattened out. But a flat universe could still be either finite or infinite. It could be like a sheet of paper that extends forever in all directions, or it could be like a flat torus, a shape you can create by connecting the opposite edges of a sheet of paper to create a boundless but finite space. In the latter case, the universe would have a kind of hidden connectivity without having an edge. So far, astronomical observations haven't revealed any signs of such cosmic connectivity. If we lived in a finite, connected universe that was smaller than our observable horizon, we might see the same distant objects appearing in multiple directions, a kind of cosmic hall of mirrors. The absence of such repeated patterns suggests that if the universe is finite, it's larger than our observable horizon. The current scientific consensus, based on observational evidence and theoretical models, strongly suggests that the universe does not have a physical edge in the conventional sense. There's no cosmic shoreline where space simply ends, no boundaries separating the universe from something else. The universe isn't expanding into anything, rather, space itself is expanding. But this leaves us with a puzzle. If the universe has no edge, what is its overall shape or topology? Is it infinite, extending forever in all directions? Or is it finite but boundless, like the surface of a sphere? To explore these possibilities, let's consider three potential global geometries for the universe: flat, closed, or open. In a flat universe with zero curvature, space follows the rules of Euclidean geometry. Such a universe could be infinite, extending forever in all directions. Alternatively, it could be finite, but without boundaries if it has a more complex topology, like a three-dimensional analog of a video game, where exiting one side of the screen causes you to reappear on the opposite side. In a closed universe with positive curvature, space is bent back on itself, like the surface of a sphere. This type of universe is finite, but has no boundaries or edges. If you could travel far enough in one direction, you would eventually return to your starting point, having circumnavigated the universe. The three-dimensional analog of this is called a hypersphere. In an open universe with negative curvature, space is shaped like a saddle or a hyperbolic surface. Such a universe would be infinite and would expand more rapidly than a flat universe. The geometry of space in this scenario leads to exponentially more volume as you move outward in any direction. Which of these geometries describes our actual universe? Observations of the cosmic microwave background radiation, particularly measurements of its fluctuations, provide strong evidence that the universe is flat or very nearly so. The lambda CDM model, the current standard model of cosmology, also incorporates this flatness. But flatness doesn't definitively tell us whether the universe is finite or infinite. For that, we need additional information about the universe's topology, the way space might be connected on the largest scales. Topology refers to the global properties of space that don't change when it's stretched or deformed. A coffee mug and a donut have the same topology because they both have one hole. You could reshape one into the other without tearing or gluing. Similarly, Different topological models of the universe describe how space might be connected on cosmic scales, potentially giving a finite universe without creating any boundaries or edges. Astronomers have searched for evidence of topological connections by looking for patterns in the cosmic microwave background radiation and in the distribution of galaxies. If the universe were finite and smaller than our observable horizon, we might see the same structures repeated in different directions or at different distances. So far, such searches haven't found compelling evidence for a compact topology, suggesting that if the universe is finite, it's larger than our observable horizon. This brings us back to the fundamental question: is the universe infinite or finite? Current observations are consistent with both possibilities, as long as a finite universe is larger than our observable horizon. Theoretical considerations also allow for either option, though some theories of cosmic inflation naturally lead to an infinite universe. An infinite universe presents its own conceptual challenges. In an infinite space with a finite age, the observable universe would represent an infinitesimally small fraction of the whole, like a single grain of sand on all the beaches of Earth. But even more extreme, beyond our cosmic horizon would lie an unlimited expanse of space, filled with galaxies, stars, and potentially even life, extending without end in all directions. Such an infinite universe would contain an infinite number of observable universe-sized regions, each with its own collection of galaxies. Given the finite number of ways particles can be arranged in a finite volume, according to quantum physics, an infinite universe would necessarily contain exact duplicates of our observable universe. Indeed, infinite exact duplicates. This mind-boggling implication of infinity leads to the cosmic doppelganger scenario we discussed earlier, where infinite copies of Earth and every person on it would exist throughout the cosmos. These duplicates would be so far away that they lie beyond our cosmic horizon, making them forever unobservable to us. Nevertheless, they would exist if the universe is truly infinite. A finite but boundless universe avoids these infinity paradoxes while still eliminating the need for an edge. In such a universe, space would curve back on itself in higher dimensions, creating a closed geometry without boundaries. This would be analogous to the surface of Earth, which is finite but has no edges. You can travel around it indefinitely without falling off. The question of whether the universe is infinite or finite connects to deeper questions about the nature of reality. Can infinity actually exist in the physical world, or is it merely a mathematical concept? If the universe is finite, what determines its size, and why does it have that particular size, rather than being larger or smaller? These questions touch on the limits of our scientific knowledge. While we can make observations and develop theoretical models, some aspects of cosmic reality may lie beyond our ability to empirically verify. The global structure of the universe, whether it's infinite or finite, whether it has a simple or complex topology, may be one of those aspects. Yet even without definitive answers, these questions drive scientific progress. They inspire new observations, new experimental techniques, and new theoretical frameworks. The quest to understand the universe's global structure continues to be an active area of research in cosmology. What we can say with confidence, based on current evidence and theoretical understanding, is that the universe does not have a physical edge in the conventional sense. There's no boundary where space abruptly ends, no cosmic shoreline beyond which nothing exists. Space may curve back on itself, or it may extend infinitely, but it doesn't simply stop. This absence of an edge has profound implications for how we conceptualize the universe. It means there's no outside to the universe, no external perspective from which the whole cosmos could be viewed. The universe encompasses all of space, time, matter, and energy. There's nothing beyond it, because beyond is not a meaningful concept when talking about the totality of existence. This comprehensive nature of the universe distinguishes it from other physical systems. Galaxies have edges, stars have surfaces, and even black holes have event horizons that mark a kind of boundary. But the universe as a whole is different. It's not embedded in some larger space, it is space. The absence of a cosmic edge also affects how we think about the universe's expansion. The universe isn't expanding into anything. There's no pre-existing empty space waiting to be filled. Rather, space itself is stretching, carrying galaxies along with it, like raisins in an expanding loaf of bread. The expansion creates new distance between objects without requiring any external space into which the universe grows. This concept challenges our intuition because we're accustomed to thinking of objects expanding into their surroundings. A balloon inflates into the air around it. An explosion spreads into the surrounding space. But the universe's expansion is fundamentally different because it involves the creation of new space rather than movement into existing space. Understanding this distinction helps clarify why asking what's beyond the universe or what it's expanding into are questions based on a misunderstanding. There is no beyond in the sense these questions assume, and the universe isn't expanding into anything external to itself. Yet despite these conceptual clarifications, the mystery of the universe's global structure remains. Is it infinite or finite? Is its topology simple or complex? Does space have hidden connections on cosmic scales? These questions may not have definitive answers at present, but they illustrate how cosmology intertwines empirical observation, mathematical modeling, and philosophical inquiry. The absence of a physical edge to the universe also connects to another fascinating question. Could our universe be part of something larger? If the universe doesn't have an edge in the conventional sense, could it still be one component of a more extensive reality? This brings us to the concept of the multiverse, the idea that our universe might be one of many universes existing as part of a larger cosmic structure. Unlike the question of an edge within our universe, the multiverse concept explores the possibility of other universes beyond our own. Not beyond in spatial terms, since our universe encompasses all of space as we know it, but beyond in a more abstract sense of existing alongside or parallel to our reality. Several theoretical frameworks in modern physics suggest the possibility of a multiverse. As we discussed earlier, eternal inflation proposes that our universe is one bubble in a vast, ever-expanding sea of inflating space, where new bubble universes continually form. String theory posits a vast landscape of possible vacuum states, each representing a different universe with different physical laws. Quantum mechanics, in some interpretations, suggests that every possible outcome of every quantum measurement occurs in some branch of reality, creating a branching multiverse of parallel worlds. These various multiverse theories provide different perspectives on what might exist beyond our universe, not in terms of a physical edge, but in terms of other realities that might exist in parallel with our own. They suggest that what we call the universe might be just one part of a much larger and more diverse reality. Of course, these multiverse theories face significant challenges, particularly regarding their empirical testability. Science traditionally relies on observations and experiments that can be repeated and verified, but other universes in a multiverse might be fundamentally unobservable from within our universe, raising questions about whether such theories can be truly scientific. Yet some versions of the multiverse theory do make potentially testable predictions. If our universe collided with another bubble universe in the past, it might have left observable imprints in the cosmic microwave background radiation. Certain quantum gravity theories suggest that other universes might leave subtle signatures in the statistics of galaxy distributions or in the polarization of the CMB. While such evidence remains elusive, the search continues, illustrating how even seemingly metaphysical questions can sometimes be approached scientifically. Whether or not the multiverse exists, the absence of a physical edge to our known universe reminds us of the limitations of our everyday intuitions when thinking about cosmic reality. Our experiences evolve in a world of distinct objects with clear boundaries, but the universe as a whole defies this framework. It has no edge where space ends, no boundary separating it from something else. It may be infinite, or it may curve back on itself in higher dimensions, but it doesn't simply stop. This boundless quality of the universe inspires both scientific inquiry and philosophical reflection. It challenges us to expand our conceptual frameworks beyond the limits of ordinary experience, to use mathematics and physics to describe realms that defy visualization, and to consider possibilities that stretch the boundaries of our understanding. In many ways, the question of the universe's edge exemplifies the broader journey of cosmology, a journey from myth and intuition to empirical observation and mathematical theory, from a bounded cosmos centered on human experience to a vast, possibly infinite reality governed by physical laws that transcend our everyday understanding. This journey continues as we explore other aspects of cosmic reality, the mysteries of dark matter and dark energy, the nature of time and space at the quantum level, the beginning and potential end of the universe. Each exploration reveals new wonders and challenges our existing conceptions, reminding us that the cosmos is not just vaster, but also stranger and more fascinating than our ancestors ever imagined. As we contemplate the absence of a physical edge to the universe, we might reflect on a profound implication. There is no exterior perspective from which the whole universe can be viewed. Unlike a globe that can be held in our hands and examined from the outside, the universe can only be experienced and studied from within. We are inescapably part of the reality we seek to understand, participants in the cosmic drama rather than external observers. This embedded perspective doesn't prevent us from gaining knowledge about the universe. Indeed, the remarkable success of modern cosmology demonstrates how much we can learn despite this limitation. But it does remind us that our understanding is always situated within the very cosmos we're trying to comprehend. Perhaps this embedded perspective is fitting. We are, after all, not separate from the universe, but an integral part of it. The atoms in our bodies were forged in ancient stars. The energy that powers our thoughts and movements has been conserved since the beginning of time. The laws that govern our biology are the same laws that govern distant galaxies. We are the universe, become conscious, matter organized into forms capable of contemplating its own existence. So while the universe may have no physical edge, no boundary where space simply ends, the exploration of this question leads us to deeper insights about the nature of reality and our place within it. It reminds us that the absence of a cosmic edge doesn't diminish the wonder of existence, but rather enhances it, revealing a universe more vast, more interconnected, and more profound than an edged cosmos could ever be. Having explored the question of whether the universe has a physical edge, we now turn to another fascinating possibility. Could our universe be one of many in a vast multiverse? This concept, once considered speculative fiction, has emerged as a serious scientific hypothesis, supported by several theoretical frameworks in modern physics. Let's explore the evidence and implications of the multiverse theory. Throughout human history, our conception of the cosmos has continuously expanded. Ancient civilizations imagined a small universe centered on Earth. The Copernican revolution placed the Sun at the center instead. Later discoveries revealed that our Sun is merely one star among hundreds of billions in the Milky Way galaxy, which itself is just one galaxy among trillions in the observable universe. Each revelation has expanded our cosmic horizon and humbled our sense of centrality. Now, we face perhaps the most mind-expanding possibility yet. Our entire universe, with its trillions of galaxies stretching across 93 billion light-years, might be just one universe among countless others in a vast multiverse. The multiverse theory suggests that what we call the universe, everything we can potentially observe, may be just a tiny fraction of a much larger and more diverse reality. This idea has traveled from the realm of science fiction and philosophy into mainstream theoretical physics, supported by several frameworks in modern cosmology and quantum physics. But what exactly is the multiverse? What evidence do we have for it? And what might it mean for our understanding of reality? The term multiverse encompasses several distinct but related concepts, each arising from different theoretical frameworks. Let's explore these different versions of the multiverse theory, beginning with the one that emerges from cosmic inflation. Inflation theory, developed in the early 1980s, proposes that the very early universe underwent a period of extraordinarily rapid expansion just a tiny fraction of a second after the Big Bang. During this brief moment, the universe expanded faster than the speed of light, doubling in size many times over in less than a billionth of a billionth of a billionth of a second. This rapid inflation explains several observed features of our universe, including its remarkable flatness and the uniformity of the cosmic microwave background radiation. But some versions of inflation theory, particularly eternal inflation, suggest that once inflation begins, it never completely stops. In this scenario, inflation ends in some regions, allowing bubble universes like our own to form, but continues in others. This ongoing inflation would continuously spawn new bubble universes, creating an ever-expanding multiverse in which our observable universe is just one bubble among countless others. These other bubble universes would be completely separate from our own, with their own space and time. We couldn't travel to them because they exist beyond our cosmic horizon, expanding away from us faster than the speed of light due to the continuing inflation of the space between bubbles. Each bubble universe might have different physical laws, different fundamental constants, and consequently, very different properties from our own universe. Some bubbles might be similar to ours, with stars, galaxies, and potentially life. Others might have slightly different physical constants, resulting in universes that could form stars, but perhaps not complex chemistry. Still others might have dramatically different physics, perhaps unable to form atoms or any complex structures at all. The multiverse would encompass this entire spectrum of possibilities, with our universe representing just one set of physical parameters among many. This inflationary multiverse concept provides an intriguing explanation for one of the most puzzling aspects of our universe: its apparent fine-tuning for the existence of life. The fundamental constants of nature in our universe, like the strength of gravity, the mass of the electron, and the strength of the nuclear forces, seem exquisitely calibrated to allow for the existence of stable atoms, long-lived stars, and the complex chemistry necessary for life. If these constants were even slightly different, the universe might be unable to support life as we know it. This fine-tuning has prompted some to see evidence of design in the universe, but the inflationary multiverse offers an alternative explanation. If there are countless bubble universes with different physical laws, we naturally find ourselves in one where the conditions happen to be right for our existence. It's not that the universe was designed for life, but rather that life evolved in a universe where the conditions happen to be suitable. This idea, known as the anthropic principle, suggests that our observations of the universe are necessarily biased by the fact that we exist to make those observations. We shouldn't be surprised to find ourselves in a universe that allows for our existence, even if such universes are extremely rare in the multiverse. After all, we couldn't exist in one of the many bubbles where the laws of physics don't allow for complex structures. The inflationary multiverse represents just one version of the multiverse concept. Another emerges from string theory, a candidate for the unified theory of physics that Einstein sought throughout the latter part of his life. String theory attempts to reconcile general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which governs the behavior of matter and energy at the smallest scales. According to string theory, the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. The way these strings vibrate determines the properties of the particles they represent, like different notes played on a violin string. This framework requires additional spatial dimensions beyond the three we experience, with these extra dimensions compactified or curled up so tightly that they're effectively invisible to us. String theory isn't a single theory, but a vast framework with many possible solutions, perhaps as many as 10 to the power of 500 different possible configurations, each representing a different possible universe with different physical laws. This vast landscape of possible universes is sometimes called the string theory multiverse. In this view, our universe with its specific physical laws is just one valley in an immense landscape of possibilities. Other universes would exist, with different configurations of the extra dimensions resulting in different physical laws and constants, like the inflationary multiverse. This framework suggests that we find ourselves in a universe compatible with our existence because we couldn't exist in the vast majority of possible universes. A third version of the multiverse emerges from quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales. According to the orthodox interpretation of quantum mechanics, particles don't have definite properties until they're measured. They exist in a superposition of multiple possible states. When a measurement is made, this superposition collapses into one definite outcome. But an alternative interpretation, proposed by Hugh Everett III in 1957, and now known as the many worlds interpretation, suggests that no collapse occurs. Instead, all possible outcomes of every quantum measurement actually happen, each in a different branch of reality. Every quantum decision point essentially creates a branching of the universe into multiple paths, creating an infinity of parallel worlds that encompass every possible sequence of events. In this quantum multiverse, there would be versions of you who made slightly different decisions in life, versions where historical events turned out differently, and versions where the laws of probability seem to be violated because extremely unlikely events actually occurred. These parallel worlds wouldn't exist in the same space as our world. They would represent alternative realities that branched off from our own at every quantum decision point. The many worlds interpretation has gained traction among physicists because it resolves certain paradoxes in quantum mechanics without introducing a special role for measurement or observers. The mathematics simply describes a branching universe where all possibilities are realized. However, it remains one interpretation among several, and the nature of quantum reality continues to be debated among physicists and philosophers. A fourth multiverse concept, more speculative than the others, is the mathematical multiverse, proposed by cosmologist Max Tegmark. This idea suggests that any mathematically consistent structure that could describe a universe actually exists as a physical reality. Our universe exists because the mathematics that describes it is consistent. Other universes would exist corresponding to other consistent mathematical structures, potentially with entirely different concepts of space, time, and physical law. This mathematical multiverse represents perhaps the most expansive and abstract version of the multiverse concept, encompassing not just variations on our universe's physics, but potentially realities governed by entirely different mathematical frameworks. These various multiverse concepts, inflationary, string theory, quantum, and mathematical, aren't mutually exclusive. Reality might incorporate elements of several or all of these frameworks, creating an almost incomprehensibly vast and diverse multiverse. Our observable universe, despite its enormous scale, might be just an infinitesimal fraction of this larger reality. But this raises a crucial question. If other universes in the multiverse are fundamentally unobservable from within our universe, is the multiverse theory truly scientific? Science traditionally relies on empirical observations and experiments that can be repeated and verified. How can we test a theory that posits the existence of universes we can never observe? This question touches on the philosophy of science and the nature of scientific theories. Some critics argue that the multiverse concept is metaphysics rather than physics. An interesting philosophical idea perhaps, but not a scientific theory because it makes no testable predictions. Others counter that a theory shouldn't be judged solely on whether we can directly observe all its elements, but rather on its explanatory power and ability to solve existing problems in physics. Proponents of the multiverse also point out that certain versions of the theory do make potentially testable predictions. If our universe collided with another bubble universe in the past, it might have left observable imprints in the cosmic microwave background radiation, a kind of cosmic bruise marking the point of impact. Several research teams have searched for such imprints, looking for unusual patterns or cold spots in the CMB that might indicate a collision with another bubble. In 2013, the Planck satellite team reported a large cold spot in the CMB that some researchers suggested might be evidence of a bubble collision. However, subsequent analysis has shown that this feature could be explained by more conventional astrophysical phenomena. The search for definitive evidence of other universes continues. Other potential tests of the multiverse theory include predictions about the distribution of galaxies, the properties of dark energy, and the pattern of primordial gravitational waves that might be detected by future observatories. These tests are indirect. They look for phenomena in our observable universe that would be more likely if the multiverse exists than if it doesn't. Even without direct observational evidence, the multiverse concept has gained traction among physicists and cosmologists because it naturally emerges from several well-established theoretical frameworks. Eternal inflation, string theory, and quantum mechanics weren't developed to explain the multiverse. They were created to address other questions in physics. Yet each of these frameworks, when followed to its logical conclusion, seems to predict a multiverse of some kind. This convergence of independent lines of reasoning suggests that the multiverse might be more than just an interesting speculation. It might represent a genuine feature of reality, even if direct evidence remains elusive. As physicist Brian Greene has noted, sometimes the most compelling evidence for an idea comes not from direct observation, but from the fact that it emerges naturally from our best theoretical frameworks. Of course, the multiverse theory faces significant challenges and criticisms. Some physicists worry that it's too convenient an explanation for fine-tuning, allowing scientists to avoid the difficult task of explaining why our universe has the specific properties it does. Others are concerned that the multiverse concept, by potentially placing some aspects of reality beyond empirical verification, blurs the line between science and metaphysics. There's also the question of simplicity. According to Occam's razor, the principle that simpler explanations are preferable to more complex ones, we should avoid multiplying entities unnecessarily. Is it simpler to posit a single universe with specific properties, or an almost infinite multiverse encompassing all possibilities? The answer isn't straightforward and depends on what we consider simple in this context. Despite these challenges, the multiverse concept continues to inspire both scientific research and philosophical reflection. It represents a profound shift in our cosmic perspective, suggesting that even our entire observable universe might be just one small part of a much larger and more diverse reality. If the multiverse exists, it would dramatically reshape our understanding of our place in the cosmos. We've already undergone several revolutions in our cosmic perspective, from Earth at the center of creation, to one planet orbiting an ordinary star, to one star among billions in one galaxy among billions. The multiverse would represent another step in this cosmic demotion, suggesting that even our entire universe might be just one among countless others. But rather than diminishing our significance, this perspective might enhance our appreciation for the remarkable coincidences that led to our existence. In a multiverse encompassing all possibilities, the particular combination of physical constants, cosmic history, and evolutionary pathways that produce conscious beings capable of contemplating the cosmos would be just one of many possibilities. Yet it's the one we experience because we couldn't exist otherwise. This perspective connects to a profound idea. The universe has become conscious of itself through us and other potential intelligent beings. The same atoms forged in ancient stars, carbon, oxygen, nitrogen, and others, now form the complex structures of our brains, allowing the universe to reflect on its own existence. In a very real sense, we are the universe thinking about itself. Even if the multiverse concept places some aspects of reality beyond our direct observation, it doesn't diminish the wonder of our existence or the value of our scientific exploration. If anything, it expands our cosmic context, inviting us to appreciate the extraordinary richness and diversity of reality. The multiverse also raises fascinating philosophical questions. If there are infinitely many universes encompassing all possibilities, Does that mean that everything that can happen does happen in some universe? Are there versions of Earth where history unfolded differently, where dinosaurs never went extinct, or where human civilization took a different path? The quantum multiverse, in particular, suggests that all possible histories might be realized in different branches of reality. These questions touch on profound issues of determinism, free will, and the nature of possibility. If all possible histories are realized in the multiverse, does that mean our own choices and actions are predetermined? Or does it mean that free will consists precisely in determining which branch of the multiverse we experience going forward? The multiverse concept also intersects with ancient philosophical questions about the existence of other worlds. Throughout history, thinkers from Democritus to Giordano Bruno have speculated about the possibility of multiple worlds or universes. The modern multiverse theory represents a scientific approach to these age-old wonderings, grounded in mathematical physics rather than pure speculation. Whether the multiverse exists or not, the concept itself illustrates how far our cosmic understanding has evolved. We've moved from a universe centered on human experience to one in which human existence is just one outcome of processes unfolding across billions of years and trillions of galaxies. The multiverse would represent another expansion of this cosmic perspective, suggesting that even our entire observable universe might be just one bubble in a vast cosmic foam. This journey from a small, human-centered cosmos to a potentially infinite multiverse reflects the remarkable capacity of the human mind to transcend its limited perspective. Using mathematics, physics, and astronomy, we've been able to explore realms far beyond our direct experience, developing theories that describe the universe on scales from subatomic particles to superclusters of galaxies, and potentially beyond to other universes. Even if we never find definitive evidence for the multiverse, the concept itself enriches our understanding of the cosmos and our place within it. It reminds us that reality might be vastly larger, more diverse, and more fascinating than we can directly observe. It challenges us to expand our thinking beyond the limits of everyday experience and to consider possibilities that stretch the boundaries of our understanding. As we continue exploring the cosmos, both through observations of our observable universe and through theoretical investigations of what might lie beyond, we should remain open to the possibility that reality is stranger and more wonderful than we can currently comprehend. The multiverse might be just one example of how the actual nature of the cosmos exceeds our limited human imagination. But even as we contemplate these vast cosmic possibilities, we shouldn't lose sight of the wonders within our observable universe. The multiverse remains a theoretical concept, while the galaxies, stars, planets, and potentially other forms of life within our cosmic horizon represent a vast realm for exploration and discovery. Within our observable universe, strange phenomena and unexplained observations might provide clues about the larger cosmic context. Anomalies in the cosmic microwave background, unexpected properties of dark energy, or unusual distributions of galaxies might hint at what lies beyond our cosmic horizon. Let's explore these cosmic anomalies and what they might tell us about the edge of the universe and potentially the multiverse beyond. In our quest to understand the universe and what might lie beyond its observable boundaries, scientists search not just for the expected, but also for the unexpected. Anomalies, oddities, and phenomena that don't quite fit our current models. These cosmic irregularities might be mere statistical flukes, or they might be signposts pointing to deeper truths about the nature of reality. Could some of these anomalies provide clues about what exists beyond the edge of our observable universe? Let's explore some of the most intriguing cosmic anomalies that have puzzled astronomers and cosmologists, and consider what they might tell us about the larger cosmos. Perhaps the most famous cosmic anomaly is the cold spot in the cosmic microwave background radiation. The CMB is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms and allowing light to travel freely through space. This ancient light has been stretched by the expansion of the universe from visible light to microwave radiation, but it still carries valuable information about the early universe. When mapped across the entire sky, the CMB shows a remarkably uniform temperature, about 2.7 Kelvin or minus 270.45 degrees Celsius, but there are tiny fluctuations in this temperature, typically just 1 part in 100,000. These fluctuations represent the seeds from which all structure in the universe, galaxies, clusters, and the cosmic web, eventually grew. The pattern of these fluctuations generally matches what our standard cosmological model predicts, except in a few places. The most notable exception is a region in the constellation Eridanus, spanning about 5 degrees of the sky, about 10 times the diameter of the full moon, where the temperature is significantly cooler than expected. This cold spot was first observed by the WMAP satellite in 2004 and later confirmed by the Planck spacecraft with even greater precision. What makes the cold spot so intriguing is its size and temperature deviation. It's much larger and cooler than we would expect from random fluctuations in the CMB. The probability of such a feature occurring by chance in our standard cosmological model is less than 1 in 50. While not impossible, this low probability has led scientists to consider alternative explanations. One of the most fascinating explanations links the cold spot to the multiverse theory. Some physicists have suggested that the cold spot might be evidence of a collision between our universe and another bubble universe in the multiverse. According to this hypothesis, when our bubble universe formed in the larger multiverse landscape, it might have collided with another bubble, creating a disturbance that we now observe as the cold spot. This bubble collision hypothesis represents an extraordinary possibility that we might be seeing direct evidence of another universe beyond our own. However, extraordinary claims require extraordinary evidence, and most cosmologists remain cautious about this interpretation. Other, more conventional explanations exist, including the possibility that the cold spot corresponds to a giant void, an unusually empty region in the distribution of galaxies, which could create a similar cooling effect through a phenomenon called the integrated Sachs-Wolf effect. Several research teams have searched for such a supervoid aligned with the cold spot. In 2015, astronomers using the Pan-STARRS telescope in Hawaii and the Dark Energy Survey did find evidence of a large void in that region, about 1.8 billion light-years across. However, subsequent studies have questioned whether this void is large enough and empty enough to fully explain the cold spot's temperature profile. The debate continues, with some scientists favoring conventional explanations, while others remain open to more exotic possibilities, like a bubble collision. What makes this anomaly so valuable from a scientific perspective is that it provides a potential test of the multiverse theory, a way to look for empirical evidence of what might exist beyond our observable universe. Another intriguing cosmic anomaly is what astronomers call dark flow, an apparent coherent motion of galaxy clusters across a large portion of the observable universe. This phenomenon was first reported in 2008 by a team analyzing data from the WMAP satellite. According to standard cosmological models, the motion of galaxy clusters should be random on very large scales, with no preferred direction. But the researchers found evidence suggesting that hundreds of galaxy clusters were moving in the same direction at speeds of up to 1,000 kilometers per second. Even more strangely, this motion appeared to be directed toward a specific point beyond the observable universe. The team proposed that this dark flow might be caused by the gravitational pull of massive structures beyond our cosmic horizon, structures so large and massive that their gravitational influence extends into our observable universe, even though we can't see them directly. If true, this would provide evidence that what exists beyond our observable universe isn't just more of the same, but potentially includes structures of extraordinary scale and mass. However, subsequent studies, particularly those using data from the Planck spacecraft, have challenged the existence of dark flow. The Planck team reported in 2013 that they found no evidence of the phenomenon within the limits of their survey. The original discoverers stand by their finding, arguing that their methodology was different and potentially more sensitive to this particular effect. The dark flow remains controversial, with no scientific consensus on whether it's a real phenomenon or an artifact of the analysis methods. But it illustrates how anomalous observations might potentially provide windows into what lies beyond our cosmic horizon. A third cosmic anomaly involves what astronomers call the axis of evil, a rather dramatic name for an alignment of patterns in the cosmic microwave background radiation. When scientists analyze the CMB using mathematical tools called spherical harmonics, essentially decomposing the temperature fluctuations into their component patterns, similar to how musical notes can be broken down into their component frequencies, they find that the larger scale patterns appear to be aligned with each other and with the plane of the solar system. This alignment, first noticed in WMAP data and later confirmed by Planck, is unexpected. According to the standard cosmological model, the patterns in the CMB should be randomly oriented, with no special alignment with our solar system or any other cosmic structure. The probability of such an alignment occurring by chance is quite low, less than 1%. Some scientists have suggested that this alignment might indicate a preferred direction or axis in the universe, challenging the cosmological principle that the universe should look the same in all directions on large scales. Others have proposed more exotic explanations, including the possibility that our universe might have collided with other universes, creating a kind of cosmic bruise that manifests as this alignment. However, more conventional explanations also exist. The alignment might be a statistical fluke, unlikely but not impossible. It might also result from systematic errors in the data analysis or from contamination by foreground emissions from our own galaxy. The fact that the alignment corresponds to the plane of the solar system raises the possibility that it might be related to the way our instruments observe the sky, rather than to a fundamental property of the universe. A fourth cosmic anomaly involves the distribution of matter on the largest scales. According to the standard cosmological model, matter should be distributed roughly uniformly when viewed on scales larger than about 300 million light-years. But some surveys have revealed structures that appear to be much larger. One such structure is the Sloan Great Wall, discovered in 2003, which spans about 1.4 billion light-years. Even more massive is the Hercules Corona Borealis Great Wall, a concentration of gamma-ray bursts suggesting a structure that might span up to 10 billion light-years, about a tenth of the diameter of the observable universe. Perhaps the most controversial large structure is what some astronomers call the Giant Ring, an apparent ring of gamma-ray bursts about 5 billion light-years across, reported in 2015. If confirmed, this would be difficult to reconcile with our current understanding of how cosmic structures form and evolve. These enormous structures push the boundaries of what our standard cosmological model can explain. They suggest that either our understanding of structure formation is incomplete, or that the universe might not be as homogeneous on large scales as we thought. Some scientists have even suggested that these structures might hint at topological features of the universe, ways in which space might be connected on the largest scales, potentially providing clues about the global structure of the cosmos beyond our observable horizon. A fifth anomaly involves the expansion rate of the universe. By measuring the redshift of distant galaxies, astronomers have determined that the universe is expanding, and not just expanding, but accelerating in its expansion, driven by a mysterious force called dark energy. But different methods of measuring this expansion rate have yielded slightly different results, creating what scientists call the Hubble tension. When astronomers measure the expansion rate using the cosmic microwave background radiation and the standard cosmological model, they get a value of about 67.4 kilometers per second per megaparsec. But when they measure it using observations of relatively nearby objects like Cepheid variable stars and supernovae, they get a value of about 73 kilometers per second per megaparsec. This discrepancy might not seem large, but it's statistically significant and has persisted despite increasingly precise measurements. This tension could be a sign that something is wrong with our cosmological model. Perhaps dark energy isn't constant but has changed over time. Perhaps there's a new form of radiation, or an exotic particle that affected the early universe. Or perhaps it hints at physics beyond our current understanding, physics that might relate to what exists beyond our observable universe. A sixth anomaly involves the fine-tuning of certain cosmological parameters. The universe appears to be extraordinarily finely tuned for the existence of complexity and life. The density of matter, the strength of the various forces, the mass of fundamental particles, and many other parameters seem precisely calibrated to allow for the formation of stars, planets, and the complex chemistry necessary for life. For example, if the strong nuclear force were just a few percent weaker, protons and neutrons wouldn't bind together, and no elements heavier than hydrogen could form. If it were just a few percent stronger, all hydrogen would fuse into helium shortly after the Big Bang, leaving no hydrogen for water and organic compounds. If the cosmological constant, which represents the energy density of empty space and drives the accelerating expansion of the universe, were slightly larger, the universe would have expanded too quickly for galaxies to form. This fine-tuning is often cited as an argument for the multiverse. In a vast multiverse with different physical laws in different regions, we naturally find ourselves in a universe compatible with our existence, even if such universes are extraordinarily rare. But the fine-tuning itself remains a cosmic anomaly that our current physics doesn't fully explain. These various anomalies, the cold spot, dark flow, the axis of evil, enormous structures, the Hubble tension, and fine-tuning, represent puzzles in our current understanding of the cosmos. Some might be resolved by more precise observations or refined analysis methods. Others might point to new physics or to aspects of the universe beyond our observable horizon. It's important to note that not all scientists agree on the significance or even the reality of some of these anomalies. Scientific progress involves debate, skepticism, and the careful evaluation of evidence. What one researcher sees as compelling evidence for new physics, another might view as a statistical fluke or a systematic error in the analysis. This scientific caution is warranted. Throughout the history of astronomy and cosmology, many apparent anomalies have eventually been explained within existing frameworks, without requiring radical revisions to our understanding. Others have indeed pointed the way to new discoveries and paradigm shifts. The key is to remain open to both possibilities, to investigate anomalies thoroughly without jumping to conclusions. What makes these cosmic anomalies particularly intriguing in the context of our exploration of the universe's edge is that they might provide indirect evidence of what lies beyond our observable horizon. If the cold spot is indeed a collision with another bubble universe, or if dark flow is caused by massive structures beyond our horizon, or if the axis of evil reflects a larger cosmic structure or topology, then these anomalies might be windows into the larger cosmos. This possibility connects to a broader point about scientific exploration. Throughout history, some of the most significant discoveries have come from investigating anomalies, observations that didn't quite fit the expected pattern. When Galileo observed the phases of Venus, when Edwin Hubble measured the redshift of distant galaxies, when Arno Penzias and Robert Wilson detected the cosmic microwave background radiation, in each case, unexpected observations led to profound revisions in our understanding of the cosmos. The anomalies we observe today might similarly lead to new insights about the universe and what might lie beyond its observable boundaries. They remind us that our current understanding is provisional, subject to revision as new evidence emerges and new theoretical frameworks are developed. They also highlight the remarkable progress we've made in observational cosmology. The fact that we can detect such subtle anomalies in the cosmic microwave background radiation or in the distribution of galaxies across billions of light years demonstrates the extraordinary precision of our instruments and analysis methods. We're able to map the universe with unprecedented detail and accuracy, revealing both its overall patterns and the subtle deviations from those patterns. As our observational capabilities continue to improve, we might resolve some of these anomalies or discover new ones. Future space telescopes, gravitational wave observatories, and neutrino detectors might reveal aspects of the cosmos that are currently hidden from view. Advanced computational methods and machine learning algorithms might identify patterns in the data that human analysis has missed. These technological and methodological advances might bring us closer to understanding what lies beyond the edge of the observable universe. While we can never directly observe regions beyond our cosmic horizon, we might find increasingly compelling indirect evidence of their nature and properties. In the meantime, cosmic anomalies serve as reminders of how much we still have to learn about the universe. They challenge our assumptions, stimulate new theoretical ideas, and drive further observations and experiments. They represent the cutting edge of cosmology, the boundary between what we know and what we're still trying to understand. They also inspire wonder and curiosity, reminding us that the cosmos is not just vaster, but also stranger and more fascinating than our ancestors ever imagined. The universe continues to surprise us, presenting puzzles that stretch our understanding and expand our cosmic perspective. As we continue our exploration of the universe's edge and what might lie beyond, we move from anomalies that might hint at larger cosmic structures to a more fundamental question about the universe itself. What is its overall shape? Is it flat, curved, or something more complex? And what might this shape tell us about the universe's boundaries and potential connections? This brings us to our next topic, the shape of the universe, finite or infinite. When we gaze up at the night sky, the universe appears to stretch endlessly in all directions. But does it truly go on forever, or does it have a finite size? And if it's finite, what shape does it take? Does it have an edge, or is it like the surface of Earth, finite yet boundless? These questions about the shape and size of the universe touch on some of the deepest mysteries in cosmology. To explore these questions, we need to understand what cosmologists mean by the shape of the universe. We're not talking about the distribution of galaxies or the cosmic web of filaments and voids. Rather, we're referring to the geometry of space itself, the underlying fabric on which the cosmic drama unfolds. Einstein's theory of general relativity tells us that space isn't just an empty container for matter and energy, but a dynamic entity that can curve and warp. The distribution of matter and energy determines the curvature of space, and this curvature determines how objects move through space. This relationship between matter, energy, and the geometry of space is at the heart of our modern understanding of gravity. On the largest scales, the overall curvature of the universe depends on its average density of matter and energy. Depending on this density, the universe could have one of three possible geometries: flat, closed, or open. A flat universe follows the rules of Euclidean geometry that we learned in school. In a flat universe, parallel lines remain parallel forever, and the sum of angles in a triangle equals 180 degrees. If you draw a huge triangle spanning billions of light years in a flat universe, its angles would still add up to exactly 180 degrees. A flat universe could be infinite, extending forever in all directions, or it could be finite if it has a more complex topology, like a three-dimensional analog of a video game screen, where exiting one side causes you to reappear on the opposite side. A closed universe has positive curvature, similar to the surface of a sphere. In such a universe, parallel lines eventually intersect, and the sum of angles in a triangle exceeds 180 degrees. If you were to travel in a straight line in a closed universe, following what physicists call a geodesic, you would eventually return to your starting point, having circumnavigated the universe. A closed universe is necessarily finite. It contains a finite amount of space and, potentially, a finite number of galaxies. An open universe has negative curvature, resembling a saddle shape or a hyperbolic surface. In this geometry, parallel lines diverge, and the sum of angles in a triangle is less than 180 degrees. An open universe is infinite, extending forever in all directions, with space expanding ever more rapidly as you move outward from any point. So which of these geometries describes our actual universe? To answer this question, cosmologists look for ways to measure the curvature of space on the largest scales. One approach involves studying the cosmic microwave background radiation, the afterglow of the Big Bang itself. The patterns of temperature fluctuations in the CMB contain information about the geometry of the universe. In a flat universe, these fluctuations should have a characteristic size on the sky. In a closed universe, they would appear larger than expected, while in an open universe, they would appear smaller. By precisely measuring these fluctuations, missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite have provided strong evidence that our universe is flat, or very nearly so. The most precise measurements to date suggest that if the universe does have any curvature, it's extremely slight, consistent with a flat geometry to within a tiny margin of error. This flatness is actually a cosmic puzzle because it requires an extraordinarily precise balance between the universe's expansion rate and its density. Without some mechanism to explain this precision, it seems like an incredible coincidence. One chance in a trillion. Cosmic inflation, the theory that the very early universe underwent a period of extraordinarily rapid expansion, provides an elegant solution to this flatness problem. During inflation, space expanded so dramatically that any initial curvature would have been flattened out, just as inflating a balloon to enormous size makes its surface appear increasingly flat to an ant walking on it. This mechanism explains why the universe appears flat today, regardless of its initial curvature. But the flatness of the universe doesn't tell us whether it's finite or infinite. A flat universe could extend infinitely in all directions, or it could be finite if it has a complex topology. This brings us to one of the most fascinating aspects of cosmic geometry: the distinction between the geometry of space, its curvature, and its topology, how it's connected. To understand this distinction, think about different two-dimensional surfaces. A flat piece of paper and the surface of a cylinder both have flat geometry. The rules of Euclidean geometry apply on both, but they have different topologies. The paper extends in all directions, at least until its edge, while the cylinder is connected differently. If you move far enough in one direction, you return to where you started. Similarly, a flat universe could have different topologies. It could be like an infinite sheet, extending forever, or it could be like a three-dimensional torus, the equivalent of a video game where moving off one edge of the screen brings you back on the opposite side, but in all three dimensions. This type of universe would be finite, but would have no boundary or edge. If our universe does have a compact topology like this, we might be able to detect it by looking for a Hall of Mirrors effect. If the universe is smaller than our observable horizon in some direction, we would see the same objects repeated at different locations in the sky, like reflections in parallel mirrors. Astronomers have searched for such patterns in the distribution of galaxies and in the cosmic microwave background radiation, but so far, no compelling evidence has been found. The absence of observable topological features suggests that if the universe is finite, it's larger than our observable horizon. This means we can't determine its overall size or shape from our observations alone. The observable universe, the spherical region from which light has had time to reach us since the Big Bang, is just a portion of the entire universe, which might be vastly larger or even infinite. The possibility of an infinite universe raises profound questions. In an infinite space with a finite age, the observable universe would represent an infinitesimally small fraction of the whole. Beyond our cosmic horizon would lie an unlimited expanse of space containing galaxies, stars, and potentially even life, extending without end in all directions. Given the finite number of ways particles can be arranged in a finite volume, according to quantum physics, an infinite universe would necessarily contain exact duplicates of our observable universe. Indeed, infinite exact duplicates. This mind-boggling implication of infinity leads to the cosmic doppelganger scenario, where infinite copies of Earth and every person on it would exist throughout the cosmos, all with the same history up to a point, after which their experiences would diverge. These copies would be so far away that they lie beyond our cosmic horizon, making them forever unobservable to us. Nevertheless, they would exist if the universe is truly infinite. This concept challenges our notion of uniqueness and identity. In an infinite universe, everything that can happen does happen, infinitely many times. A finite but boundless universe avoids these infinity paradoxes while still eliminating the need for an edge. In such a universe, space would curve back on itself in higher dimensions, creating a closed geometry without boundaries. This would be analogous to the surface of Earth, which is finite but has no edges. You can travel around it indefinitely without falling off. The question of whether the universe is infinite or finite connects to deeper questions about the nature of reality. Can infinity actually exist in the physical world, or is it merely a mathematical concept? If the universe is finite, what determines its size, and why does it have that particular size rather than being larger or smaller? These questions touch on the limits of our scientific knowledge. While we can make observations and develop theoretical models, some aspects of cosmic reality may lie beyond our ability to empirically verify. The global structure of the universe, whether it's infinite or finite, whether it has a simple or complex topology, may be one of those aspects. Yet even without definitive answers, these questions drive scientific progress. They inspire new observations, new experimental techniques, and new theoretical frameworks. The quest to understand the universe's global structure continues to be an active area of research in cosmology. One approach to investigating the universe's shape involves studying its overall density. According to Einstein's equations, the density of matter and energy determines the curvature of space. If the density exactly equals a critical value, about 6 hydrogen atoms per cubic meter on average, the universe is flat. If the density exceeds this critical value, the universe is closed and finite. If the density is less than the critical value, the universe is open and infinite. Measurements of the cosmic microwave background radiation, combined with observations of distant supernovae and the distribution of galaxies, indicate that the total density of the universe is incredibly close to the critical value, within a few percent. This includes not just ordinary matter like stars and galaxies, but also dark matter and dark energy. Dark matter, which makes up about 27% of the universe's content, doesn't interact with light, but exerts gravitational influence on visible matter. Its presence is inferred from various observations, including the rotation curves of galaxies, the motions of galaxy clusters, and the pattern of temperature fluctuations in the CMB. Dark energy, which accounts for about 68% of the universe's content, is even more mysterious. It appears to permeate all of space and drives the accelerating expansion of the universe. Its nature remains one of the biggest puzzles in modern physics, with implications for our understanding of the universe's shape and fate. The density of dark energy appears to be nearly constant throughout space and time. This constancy gives it a special property. As the universe expands, the total amount of dark energy increases, since there's more space, while the density of matter decreases, since the same amount of matter is spread over a larger volume. This means that dark energy has an increasingly dominant influence on the universe's expansion as time passes. The presence of dark energy complicates the relationship between the universe's density and its geometry. In a universe without dark energy, a density equal to the critical value would result in a flat universe that expands forever, but at an ever-decreasing rate. However, with dark energy, a flat universe actually accelerates in its expansion, with galaxies receding from each other at an ever-increasing pace. This acceleration affects our understanding of the universe's global structure. In a flat or open universe dominated by dark energy, space extends infinitely in all directions and will continue to expand forever. In a closed universe, the situation is more complex. If the positive curvature is strong enough, it might eventually overcome the effect of dark energy, causing the universe to stop expanding and collapse in a big crunch. But if dark energy dominates, even a closed universe might expand forever, despite its finite volume. Current observations strongly favor a flat universe dominated by dark energy, which will expand forever at an accelerating rate. But these observations don't tell us whether the universe is infinite or finite. They only constrain its curvature and expansion history. Another approach to investigating the universe's shape involves looking for patterns in the cosmic microwave background radiation that might indicate a specific topology. For example, if the universe were shaped like a three-dimensional torus, a donut shape in higher dimensions, we might see patterns in the CMB that repeat at regular intervals, like wallpaper. Scientists have searched for such patterns using data from the WMAP and Planck satellites. These searches have ruled out many simple topological models for the universe, suggesting that if the universe does have a compact topology, it's more complex than the simplest models predict. The universe's shape also relates to its origin. Most cosmologists believe that the universe began in the Big Bang, not an explosion in space, but an expansion of space itself from an extremely hot, dense state. But what caused this initial expansion? What determined the universe's initial size and shape? Inflation theory provides a potential answer. According to this theory, the very early universe underwent a period of exponential expansion, doubling in size many times over, in less than a billionth of a billionth of a billionth of a second. This rapid inflation would have erased any initial curvature, resulting in the flat universe we observe today. Inflation also explains why the universe appears so uniform on large scales. Regions of space that are now separated by billions of light years were close enough to interact before inflation drove them apart, allowing them to reach the same temperature and density. This explains the remarkable uniformity of the cosmic microwave background radiation, which has the same temperature to within 1 part in 100,000 across the entire sky. Some versions of inflation theory, particularly eternal inflation, suggest that inflation never completely stops. It ends in some regions, allowing bubble universes like our own to form, but continues in others. This ongoing inflation would continuously spawn new bubble universes, creating an ever-expanding multiverse in which our observable universe is just one bubble among countless others. In this multiverse scenario, questions about the shape and size of the universe become even more complex. Our observable universe would be just a tiny portion of our bubble universe, which itself would be just one bubble in a vast, perhaps infinite multiverse. Each bubble might have different physical laws, different geometries, and different topologies. The multiverse concept represents a profound shift in how we think about cosmic reality. Rather than a single universe with a specific shape and size, there might be a vast ensemble of universes with diverse properties. Our observable universe would be just one small part of this larger cosmic landscape. Whether or not the multiverse exists, our exploration of the universe's shape reminds us of the remarkable progress we've made in understanding the cosmos. From ancient cosmologies that depicted Earth at the center of a small, bounded universe, we've evolved to a perspective that encompasses billions of galaxies spread across billions of light years, potentially within an infinite expanse of space or a finite but boundless geometry. This evolution in our cosmic perspective has been driven by a combination of observational evidence and theoretical insight. From Galileo's telescope to the Hubble Space Telescope, from Newton's laws of motion to Einstein's theory of relativity, we've continually refined our understanding of the universe's structure and dynamics. Yet profound questions remain. Is the universe infinite or finite? If it's finite, what is its overall topology? How does its shape relate to its origin in the Big Bang and its eventual fate? These questions continue to drive research in cosmology, inspiring new observations, experiments, and theoretical models. As we contemplate these cosmic questions, we might reflect on their philosophical implications. The shape of the universe isn't just a scientific issue, but also a philosophical one, touching on fundamental questions about the nature of reality, the limits of knowledge, and our place in the cosmos. If the universe is infinite, it challenges our ability to comprehend totality. The concept of everything that exists becomes too vast for our finite minds to truly grasp. If it's finite but boundless, it challenges our intuitive notion of an edge or boundary to physical reality. Either way, the universe's shape represents a concept that extends beyond our everyday experience, requiring us to use mathematics and physics to describe what we cannot directly visualize. This transcendence of ordinary intuition is a hallmark of modern cosmology. The universe as revealed by science is not just vaster, but also stranger and more fascinating than our ancestors ever imagined. It defies simple categories and challenges us to expand our conceptual frameworks. Whether the universe is flat or curved, finite or infinite, its exploration continues to inspire wonder and curiosity. The question of the universe's shape represents one of the great frontiers in our quest to understand the cosmos and our place within it. As we continue our journey exploring the edge of the universe, we turn from questions about its present shape to considerations of its ultimate fate. How will the universe evolve in the distant future? Will it expand forever, collapse back on itself, or meet some other cosmic destiny? These questions about the universe's fate are intimately connected to its shape and composition, forming the next chapter in our cosmic exploration. Throughout human history, cultures around the world have imagined how the world might end, in fire or ice, with a bang or a whimper. These apocalyptic visions typically focused on Earth alone, but modern cosmology has expanded our perspective to consider the ultimate fate of the entire universe. What will happen in the far distant future, trillions upon trillions of years from now? Will the universe expand forever, collapse back on itself, or meet some other cosmic destiny? These questions about the universe's fate are intimately connected to its shape, composition, and dynamics. By studying how the universe has evolved so far and measuring the forces driving its expansion, cosmologists can project these trends into the future, offering glimpses of how the cosmic story might ultimately unfold. For most of the 20th century, cosmologists believed the universe's fate hinged primarily on a simple question: is there enough matter in the universe for gravity to eventually halt and reverse its expansion? If yes, the universe would eventually stop expanding and begin contracting, ultimately collapsing in a big crunch, a mirror image of the Big Bang. If no, the universe would expand forever, gradually cooling and thinning out in a big freeze or heat death scenario. This simple dichotomy was based on Einstein's equations of general relativity and the assumption that the universe contains only matter, both ordinary and dark, and radiation. In such a universe, the expansion rate would gradually slow due to the gravitational attraction between galaxies, and the ultimate fate would depend on whether this deceleration eventually reversed the expansion. But in 1998, observations of distant supernovae revealed something astonishing. The expansion of the universe isn't slowing down, it's speeding up. This accelerating expansion, attributed to a mysterious force called dark energy, completely transformed our understanding of the universe's future. Dark energy appears to be a property of space itself. Unlike matter, which becomes more dilute as the universe expands, the density of dark energy remains constant as space stretches. This means that as the universe grows larger, the total amount of dark energy increases, while its density stays the same. This unique property gives dark energy an increasingly dominant influence on the universe's expansion as time passes. With dark energy driving an accelerating expansion, the simplest and most widely accepted model for the universe's fate is what cosmologists call the Big Freeze, or heat death. In this scenario, the universe expands forever at an ever-increasing rate, with galaxies moving apart more and more rapidly. Let's trace how this scenario might unfold over the vastness of cosmic time. Keep in mind that the universe is currently about 13.8 billion years old. The timescales we're about to explore are many orders of magnitude longer. In about 4 billion years from now, still the relatively near future in cosmic terms, our Milky Way galaxy will collide and merge with the neighboring Andromeda galaxy. This won't be a catastrophic collision in the conventional sense. Stars are so far apart that they rarely hit each other directly. Instead, the two galaxies will pass through each other, their stars intermingling, until they eventually settle into a single larger elliptical galaxy that astronomers have already named Milkomeda. Over the next few 100 billion years, similar mergers will bring together all the galaxies in our local group. The small cluster of galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies. The result will be a single enormous elliptical galaxy containing all the stars from the former local group members. But what about more distant galaxies? Here, dark energy plays a crucial role. As the universe's expansion accelerates, galaxies outside our local group move away from us faster and faster. Currently, we can observe galaxies out to distances of billions of light years. But in about 100 billion years, all galaxies outside our local group will be receding faster than the speed of light due to the expansion of space itself. This doesn't violate Einstein's theory of relativity, which states that nothing can travel through space faster than light. The galaxies aren't moving through space that quickly. Rather, the space between galaxies is expanding so rapidly that the total separation speed exceeds the speed of light. This is allowed in general relativity because it's space itself that's expanding, not objects moving through space. The consequence of this accelerating expansion is that galaxies outside our local group will gradually disappear from view. Their light, traveling through ever-expanding space, will be stretched to longer and longer wavelengths and will become too faint to detect. About 100 billion years from now, future astronomers in Milkomeda will see only a single enormous galaxy surrounded by empty darkness. All evidence of the broader universe, the billions of galaxies we can see today, will have vanished beyond their cosmic horizon. This disappearance of the observable universe has profound implications. Future civilizations might have no way to learn about the vast cosmos beyond their local galaxy. The evidence that led us to discover the Big Bang, the expansion of the universe, and dark energy will have faded away. Without these observations, future scientists might develop very different ideas about the nature and history of the universe. This reminds us of how fortunate we are to live in what some cosmologists call the observable era of the universe, a time when we can still see distant galaxies and detect the cosmic microwave background radiation, allowing us to piece together the universe's history and structure. As we move further into the future, stars will continue to form within Milkomeda for perhaps another trillion years, using up the available gas and dust. But eventually, star formation will cease as the raw materials are depleted. The existing stars will burn through their nuclear fuel and reach the end of their lives, becoming white dwarfs, neutron stars, or black holes. White dwarfs and neutron stars will gradually cool over trillions of years, fading from bright stellar objects to cold, dark remnants. Black holes will very slowly evaporate through a process called Hawking radiation, named after physicist Stephen Hawking, who predicted it. But this evaporation happens extremely slowly. A black hole with the mass of our Sun would take about 10 to the power of 67 years to completely evaporate. That's a 1 followed by 67 zeros. An almost incomprehensibly long time. By about a trillion years from now, 10 to the power of 24 years, even the largest stars that formed will have burned out, and the universe will enter what cosmologists call the degenerate era. During this era, the only sources of energy will be the gradually cooling stellar remnants, white dwarfs, neutron stars, and black holes. The universe will grow increasingly dark and cold. Occasionally, chance encounters between stellar remnants might produce momentary bursts of energy, but these will become increasingly rare as the accelerating expansion carries objects farther apart. The matter that once formed bright galaxies will be scattered across an ever-expanding, ever-darkening cosmos. As we move even further into the future, to around 10 to the power of 40 years, even the protons and neutrons that make up atomic nuclei might begin to decay. This proton decay is predicted by some theories in particle physics, though it hasn't been observed experimentally. If it occurs, all ordinary matter would eventually dissolve. leaving only a diffuse sea of elementary particles and radiation, growing ever more dilute as the universe continues to expand. By the time we reach timescales of 10 to the power of 100 years and beyond, even the supermassive black holes at the centers of galaxies will have evaporated through Hawking radiation. The universe will consist almost entirely of extremely low-energy photons, neutrinos, and other elementary particles, spread across unimaginably vast distances. The temperature will approach absolute zero, and entropy, a measure of disorder, will reach its maximum. This is the ultimate heat death of the universe, a state of perfect uniformity where no work can be done and no complex structures can exist. This big freeze scenario, based on our current understanding of physics and cosmology, represents a rather bleak ultimate fate for the universe. All stars burn out, all structures dissolve, and even black holes eventually evaporate, leaving a cold, dark, nearly empty cosmos expanding forever at an accelerating rate. But this isn't the only possible fate for the universe. Alternative scenarios exist, each based on different assumptions about the nature of dark energy and other aspects of physics. Let's explore some of these alternative cosmic destinies. One possibility is the Big Rip. In this scenario, dark energy isn't constant, but grows stronger over time, eventually becoming so powerful that it tears apart all structures in the universe: galaxies, stars, planets, atoms, and even subatomic particles. The acceleration of the universe's expansion becomes so extreme that even the fabric of space-time itself is ripped apart. The timing of this Big Rip depends on how quickly dark energy strengthens. In some models, it could happen as soon as 20 billion years from now. In others, it might take trillions of years. The key feature of this scenario is that the universe doesn't end in a whimper, but in a violent tearing apart of all matter and space itself. Another alternative is the Big Crunch. Although current observations strongly suggest an accelerating expansion, it's possible that dark energy might change its behavior in the distant future. If it were to weaken or even transform into an attractive force, the universe's expansion could eventually halt and reverse. In this scenario, after trillions of years of expansion, the universe would begin to contract. Galaxies would move closer together, eventually merging. The cosmic microwave background radiation would be blue-shifted, becoming hotter and more energetic. In the final moments, all matter in the universe would collapse into an incredibly hot, dense state similar to the Big Bang, completing a full cosmic cycle. This idea of a cyclic universe, oscillating between Big Bangs and Big Crunches, has fascinated cosmologists for decades. Could our universe be just one cycle in an eternal series of expansions and contractions? The current evidence for dark energy makes this scenario seem unlikely, but we can't completely rule it out, especially over the immense timescales we're considering. A variation on the cyclic universe is the Big Bounce model. In this scenario, as the universe contracts toward a big crunch, quantum gravitational effects prevent it from collapsing to an infinitely dense singularity. Instead, the contraction halts and reverses, causing the universe to bounce into a new expansion phase, effectively a new Big Bang. Some versions of the Big Bounce model suggest that the fundamental constants of nature might change slightly with each bounce, potentially creating different physical conditions in each cycle. Others propose that the bounce preserves the entropy accumulated in the previous cycle, meaning that each new universe would be larger and more disordered than its predecessor. Another intriguing possibility is what cosmologists call the Big Slurp, or vacuum decay. According to quantum field theory, the vacuum of space might not be in its lowest energy state. Instead, it might be in a false vacuum, a metastable state that could tunnel to a lower energy true vacuum. If this vacuum decay occurred at any point in the universe, it would create a bubble of true vacuum that would expand at nearly the speed of light. Inside this bubble, the laws of physics would be radically different, likely incompatible with the existence of matter as we know it. The boundary of this bubble would be a wall of destruction, obliterating everything in its path as it converted the false vacuum to true vacuum. The unsettling aspect of this scenario is that, unlike the Big Freeze or Big Rip, which would take billions or trillions of years, vacuum decay could happen at any moment without warning. We wouldn't see it coming, as the bubble would expand nearly at the speed of light, and we couldn't escape it for the same reason. However, the fact that the universe has existed for billions of years suggests that vacuum decay is unlikely to occur soon, if it can happen at all. Yet another possibility is the Big Bounce from eternal inflation. In some versions of inflation theory, our universe might be one bubble among many in a larger multiverse that undergoes eternal inflation. These bubbles might occasionally collide, potentially triggering dramatic changes in the affected regions. The fate of the universe might also be influenced by discoveries in fundamental physics that we haven't yet made. Our current understanding is based on general relativity and quantum mechanics, theories that work extraordinarily well in their respective domains, but are famously incompatible with each other. A unified theory of quantum gravity might reveal new phenomena that could dramatically alter our predictions for the universe's future. For example, string theory and loop quantum gravity, two candidates for a theory of quantum gravity, suggest that space and time might have a discrete, granular structure at the smallest scales. This quantum space-time might behave very differently from the continuous space-time of general relativity, particularly under the extreme conditions of cosmic beginnings and endings. Some approaches to quantum gravity also suggest the possibility of new dimensions or connections between different regions of space-time. These exotic structures might allow for transitions between different universes or cycles, opening up possibilities beyond the scenarios we've discussed. It's also worth noting that our understanding of dark energy remains limited. We've observed its effects, the accelerating expansion of the universe, but we don't know what it actually is. Is it a cosmological constant, as Einstein originally proposed? Is it a dynamic field that changes over time? Or is it something else entirely, perhaps a manifestation of modified gravity or extra dimensions? Different models of dark energy predict different fates for the universe. If it's a true cosmological constant, the Big Freeze scenario is most likely. If it varies over time, we might see a Big Rip or even a Big Crunch. Our ongoing observations of the universe's expansion, particularly using distant supernovae and other standard candles that allow us to measure cosmic distances, will help constrain these models and clarify the universe's likely fate. But perhaps the most profound question about the universe's fate isn't about the physical end, but about the fate of consciousness and complexity. If the universe is destined for a heat death, with all matter and energy spreading out into a nearly perfect uniformity, does that mean the end of all life, intelligence, and civilization? Not necessarily. According to some theorists, Freeman Dyson, a physicist known for his creative ideas, suggested that an intelligent civilization might be able to survive indefinitely, even in an ever-cooling universe, by constantly reducing its energy consumption and operating at increasingly lower temperatures. While individual thoughts would take longer and longer to process, subjective time might remain constant from the civilization's perspective. Other thinkers have speculated about the possibility of creating baby universes, initiating new Big Bangs in laboratory conditions, as a way for advanced civilizations to escape the death of their own universe. While this remains firmly in the realm of speculation, it illustrates how the question of the universe's fate intertwines with profound questions about the future of intelligence and consciousness. Some philosophers and physicists have also suggested that if the multiverse exists, with infinite variations of physical laws and constants, there might be universes with different fates. Some might end in a big crunch, others in a big freeze or big rip. In this view, the question isn't just, how will the universe end, but how many different ways can universes end? This perspective reminds us of the remarkable fact that we can even ask these questions about cosmic endings. From our tiny planet, orbiting an ordinary star in one galaxy among billions, we've developed the intellectual and technological tools to contemplate the ultimate fate of the entire cosmos. This capacity for understanding This ability to project the universe's evolution across timescales vastly longer than human existence is one of the most remarkable features of human consciousness. Our exploration of the universe's fate also highlights the extraordinary progress we've made in cosmology over the past century. From a time when we didn't know there were other galaxies beyond the Milky Way, we've advanced to detailed models of the universe's birth, evolution, and potential endings, supported by precise observations and sophisticated theoretical frameworks. Yet we should remain humble about these projections. Throughout the history of science, our understanding has been repeatedly revised as new evidence and theories have emerged. The discoveries of dark matter and dark energy, which together make up about 95% of the universe's content, remind us that fundamental aspects of cosmic reality might still await discovery. The universe has surprised us before and will likely surprise us again. Our current projections of its fate, while based on the best available evidence and theory, remain provisional, subject to revision as our understanding deepens. The ultimate fate of the universe might be even stranger and more fascinating than any of the scenarios we've discussed. As we contemplate these cosmic endings, we might reflect on their philosophical implications. The heat-death scenario, in particular, presents a profound existential challenge. If the universe ultimately dissolves into a state of perfect uniformity and maximum entropy, what meaning can we find in the cosmic story? One response is to find meaning in the journey rather than the destination, in the remarkable complexity, beauty, and consciousness that emerge during the universe's long middle chapter, even if they don't last forever. The fact that atoms forged in ancient stars could organize themselves into beings capable of contemplating the cosmos is extraordinary, regardless of the universe's ultimate fate. Another perspective comes from considering the truly vast timescales involved. The heat death or Big Rip would occur trillions upon trillions of years in the future. Timescales so immense that they dwarf not just human history, but the entire current age of the universe. On such scales, even phenomena that seem permanent from our perspective are revealed as transient, part of the universe's ongoing evolution. Whether the universe ends in ice, a heat death, fire, a big crunch, or cosmic disruption, a big rip, the quest to understand its ultimate fate represents one of humanity's most remarkable intellectual journeys. From our tiny cosmic perspective, we've developed theories that allow us to project the universe's evolution across unimaginable timescales, revealing potential endings that challenge our understanding and inspire wonder. As we continue exploring the cosmos through observation, experiment, and theory, we'll refine our understanding of these cosmic endings. Future discoveries might reveal new possibilities or help us determine which of the currently proposed scenarios is most likely. But regardless of the specific outcome, the exploration itself, this cosmic journey from ignorance to understanding, represents one of the greatest achievements of our species. While the universe's end might lie trillions of years in the future, our exploration of cosmic horizons continues in the present. As we look ahead to the coming decades and centuries, new telescopes, observatories, and theoretical approaches promise to expand our view of the cosmos and deepen our understanding of its structure, history, and potential future. This brings us to our final topic, the future of exploration, peering beyond the edge of the universe. Throughout human history, we've been explorers, venturing beyond the horizons of our knowledge into the unknown. From the first humans, who gazed at the night sky with wonder, to modern astronomers peering into the depths of the cosmos with sophisticated telescopes, our journey to understand the universe has been marked by an insatiable curiosity about what lies beyond the current limits of our perception and comprehension. We've come an extraordinarily long way in this cosmic journey. Just a century ago, astronomers didn't know that galaxies beyond the Milky Way existed. Today, we've mapped billions of galaxies, traced cosmic history back to the afterglow of the Big Bang, detected ripples in space-time from colliding black holes, and developed theories that describe the universe's evolution across 14 billion years. Yet for all this progress, we still face fundamental limits in our ability to observe and understand the cosmos. The The edge of the observable universe, our cosmic horizon, marks the boundary of what we can directly see. Beyond this horizon lie regions of space from which light hasn't had time to reach us since the Big Bang, and in the context of an accelerating universe, some regions will remain forever beyond our observational reach, no matter how long we wait or how powerful our telescopes become. But science has a remarkable capacity to transcend apparent limitations. Even when direct observation is impossible, indirect measurements, theoretical models, and creative experimental approaches can provide glimpses of what might lie beyond the observable. As we look to the future of cosmic exploration, new technologies and methodologies promise to push the boundaries of what we can observe and understand about the universe and what might exist beyond its edge. Perhaps the most exciting frontier in observational cosmology involves new ways to observe the universe. Throughout most of human history, our cosmic observations were limited to visible light. In the 20th century, we expanded our view to include other forms of electromagnetic radiation, from radio waves to gamma rays, each revealing different aspects of cosmic phenomena. But light, in all its forms, has limitations. It can be blocked, scattered, or absorbed, and it only carries certain types of information. In recent years, we've begun to detect the universe through entirely new messengers, particles and waves that are not part of the electromagnetic spectrum. These new windows on the cosmos promise to reveal aspects of the universe that have been hidden from view and potentially provide indirect evidence of what lies beyond our observable horizon. One of the most significant breakthroughs came in 2015 with the first detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, or LIGO. These ripples in space-time, predicted by Einstein's general relativity, are created when massive objects accelerate, particularly in extreme events like the collision of black holes or neutron stars. Unlike light, gravitational waves pass through matter almost completely unimpeded. They can travel across the universe without being blocked, scattered, or absorbed. This means they can carry information from regions that are otherwise invisible to us, including the interiors of collapsing stars, the environments around black holes, and potentially even the first fraction of a second after the Big Bang. Current gravitational wave detectors are limited to detecting relatively local events within our galaxy or nearby galaxies. But future observatories, both on Earth and in space, will have much greater sensitivity. The planned Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory, will be able to detect gravitational waves from supermassive black hole mergers throughout the observable universe, and potentially even from the inflationary period just after the Big Bang. If we could detect gravitational waves from inflation, it would give us a window into the universe just a tiny fraction of a second after its birth, far earlier than we can see with electromagnetic radiation. This might reveal clues about the universe's initial conditions, the nature of inflation, and potentially even evidence for a multiverse. Another promising cosmic messenger is neutrinos, nearly massless particles that interact very weakly with matter. Like gravitational waves, neutrinos can pass through enormous amounts of matter without being stopped, allowing them to carry information from otherwise inaccessible regions. We've already detected neutrinos from the Sun and from a supernova in a nearby galaxy, SN 1987A, but future neutrino observatories will be far more sensitive. They might be able to detect the cosmic neutrino background, neutrinos released about 1 second after the Big Bang, when the universe cooled enough for these particles to stop interacting frequently with other matter. If detected, this neutrino background would show us the universe at a much earlier stage than the cosmic microwave background radiation, potentially revealing new insights about the early universe and what might lie beyond our cosmic horizon. Ultra-high energy cosmic rays represent another potential window into extreme cosmic phenomena. These are particles, mostly protons, that have been accelerated to extraordinarily high energies by some of the most powerful processes in the universe. The most energetic cosmic ray ever detected had an energy comparable to a baseball traveling at 90 miles per hour, all concentrated in a single subatomic particle. The origins of these ultra-high-energy cosmic rays remain mysterious. They might be accelerated by supermassive black holes, gamma-ray bursts, or other extreme cosmic events. Future observatories like the planned Giant Radio Array for Neutrino Detection, GRAND, will detect these particles with unprecedented sensitivity, potentially revealing their sources and the physical processes that accelerate them to such remarkable energies. While these new cosmic messengers, gravitational waves, neutrinos, and cosmic rays, might not directly show us what lies beyond the edge of the observable universe, they could provide indirect evidence. For example, if eternal inflation theory is correct, our universe might occasionally collide with other bubble universes in the multiverse. Such collisions might leave subtle imprints in the cosmic microwave background radiation or potentially produce distinctive patterns of gravitational waves that future observatories could detect. Similarly, certain theories of quantum gravity predict specific patterns in the gravitational wave background or in the spectrum of cosmic neutrinos. By testing these predictions through precise observations, we might find evidence for theoretical frameworks that describe what lies beyond our cosmic horizon. In addition to these new observational approaches, advances in our ability to observe electromagnetic radiation will continue to deepen our understanding of the cosmos. The James Webb Space Telescope, launched in December 2021, represents a quantum leap in our ability to observe the infrared universe. With its large mirror and sophisticated instruments, Webb can see farther back in time than any previous telescope, potentially observing the first galaxies that formed just a few 100 million years after the Big Bang. Future observatories will push these boundaries even further. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will combine a Hubble-sized mirror with a wide-field view, allowing it to survey vast regions of the sky with unprecedented detail. This will enable more precise measurements of dark energy, potentially revealing how this mysterious force has evolved over cosmic time, and providing clues about the universe's ultimate fate. On the ground, enormous telescopes with mirrors spanning 30 meters or more are being constructed. The extremely large telescope in Chile, with a mirror 39 meters in diameter, will collect 13 times more light than the largest existing optical telescopes. This will allow it to study the atmospheres of exoplanets, observe the first stars and galaxies in unprecedented detail, and test the fundamental laws of physics through precise cosmic measurements. In radio astronomy, the Square Kilometre Array will combine thousands of dishes and millions of antennas across Australia and South Africa to create the world's largest radio telescope. With sensitivity 50 times greater than current radio telescopes, it will be able to detect extremely faint signals from the early universe, potentially mapping the cosmic dawn when the first stars and galaxies formed. These observational advances will be complemented by revolutionary computational approaches. Machine learning and artificial intelligence are already transforming how astronomers analyze the vast amounts of data generated by modern telescopes. These techniques can identify patterns that might be missed by human researchers, potentially revealing subtle signatures of phenomena beyond our cosmic horizon. Quantum computing, still in its infancy, promises to tackle computational problems that are intractable for classical computers. This could enable more sophisticated simulations of cosmic evolution, exploring how different models of physics beyond our current understanding might manifest in observable phenomena. Theoretical physics will also continue to evolve, potentially providing new frameworks for understanding what might lie beyond the observable universe. The quest for a theory of quantum gravity, a unified description of gravity and quantum mechanics, remains one of the greatest challenges in theoretical physics. Various approaches, including string theory, loop quantum gravity, and causal set theory, offer different perspectives on how space and time might behave at the smallest scales and under the most extreme conditions. These theories often suggest that our universe might be one component of a larger reality, whether a multiverse of bubble universes, a cyclic cosmos that bounces from Big Bang to Big Crunch and back again, or a holographic projection of information encoded on a lower dimensional boundary. While such ideas might seem speculative, they emerge from serious attempts to reconcile our best theories of physics and could potentially be tested through precise observations of cosmic phenomena. The interplay between theory and observation has always been the engine of scientific progress. New theoretical insights suggest novel observations, and unexpected observations inspire new theoretical frameworks. This dialectic will continue to drive our exploration of the cosmos, potentially revealing aspects of reality that we can't currently imagine. But we should also acknowledge the possibility that some aspects of cosmic reality might remain permanently beyond our observational reach. The accelerating expansion of the universe, driven by dark energy, means that regions beyond our current cosmic horizon will never become visible to us, no matter how long we wait or how powerful our instruments become. In fact, galaxies that we can see today will eventually disappear from view as the expansion carries them beyond our horizon. This limitation doesn't mean we should stop exploring. Even if we can never directly observe what lies beyond the edge of the observable universe, we can continue to refine our theoretical understanding and look for indirect evidence. The history of science is full of examples where phenomena that seemed unobservable were eventually detected through ingenious experimental approaches or theoretical insights. For example, atoms were once considered purely theoretical constructs, too small to ever be directly observed. Today, we can not only detect individual atoms, but manipulate them with precision. Black holes were once mathematical curiosities emerging from Einstein's equations. Now we've directly imaged a black hole's shadow and detected gravitational waves from black hole mergers. What seems unobservable today might become accessible tomorrow through advances in technology or conceptual breakthroughs. Moreover, there's still so much to discover within our observable universe. We've identified trillions of galaxies, but studied only a tiny fraction in detail. We've detected thousands of exoplanets, but have barely begun to characterize their atmospheres and potential habitability. We've observed cosmic phenomena like fast radio bursts, ultra-high energy cosmic rays, and gamma-ray bursts, but don't fully understand their origins or mechanisms. The observable universe, with its estimated 2 trillion galaxies, represents an almost unimaginably vast realm for exploration. Even with our most powerful telescopes and instruments, we've barely scratched the surface of what's out there. There are countless discoveries waiting to be made, mysteries to be solved, and wonders to be revealed within the boundaries of what we can observe. This rich frontier for exploration within our cosmic horizon doesn't diminish our curiosity about what might lie beyond. It's in our nature to wonder about the unseen, to imagine what might exist past the boundaries of our knowledge. This cosmic curiosity, this desire to understand not just what we can see but the ultimate nature of reality, has been a driving force in human intellectual history. From a philosophical perspective, our exploration of the universe's edge and what might lie beyond touches on profound questions about the nature of knowledge and the limits of understanding. Can we know things that we can't directly observe? How do we evaluate theories that make predictions about unobservable realms? What constitutes evidence for phenomena beyond our observational horizon? These questions connect cosmology to epistemology, the branch of philosophy concerned with the nature and scope of knowledge. Throughout history, philosophers have debated whether and how we can know about things beyond our direct experience. Modern cosmology brings these ancient philosophical questions into a scientific context, where mathematical models and indirect observations provide ways to reason about what might exist beyond the limits of direct perception. The future of cosmic exploration will likely involve a continued dialogue between these philosophical considerations and scientific methodologies. As our observations become more precise and our theories more comprehensive, we'll continue to push the boundaries of what we can know about the universe and what might lie beyond its edge. This journey of discovery will require not just technological and theoretical advances, but also a spirit of wonder, curiosity, and intellectual humility. We should be open to the possibility that the universe is stranger and more fascinating than we currently imagine. that our most cherished theories might need revision in light of new evidence, and that some aspects of cosmic reality might permanently exceed our full comprehension. Such humility doesn't diminish the value of our cosmic exploration. On the contrary, it enhances it, reminding us that each new discovery isn't an endpoint, but a stepping stone to deeper understanding. The edge of the universe isn't just a physical boundary, but a threshold of knowledge, a horizon that recedes as we approach it, revealing new vistas and new questions with each advance. This ongoing exploration connects us to a heritage of cosmic curiosity that spans human history. From the ancient astronomers who tracked the movements of planets to modern cosmologists who map the large-scale structure of the universe, we've been driven by a desire to understand our place in the cosmos and what lies beyond our immediate perception. Modern science has revealed a universe far vaster, more ancient, and more fascinating than our ancestors could have imagined. The hundreds of billions of galaxies, each containing hundreds of billions of stars, spread across billions of light-years of space, represent a cosmic scale that defies our everyday intuition. The 14-billion-year history of the universe, from the Big Bang to the complex structures we see today, reveals a cosmic evolution of extraordinary richness and complexity. Yet there's still so much we don't know. What is dark matter? What is dark energy? Why does the universe have the specific laws and constants that it does? What happened in the first fraction of a second after the Big Bang? What lies beyond our cosmic horizon? These questions drive ongoing research in cosmology, astrophysics, and particle physics, inspiring new observations, experiments, and theoretical frameworks. As we look to the future of cosmic exploration, we can be confident that we'll continue to push the boundaries of our understanding. New telescopes, observatories, and experimental approaches will reveal aspects of the universe that are currently hidden from view. Advanced computational techniques will extract more information from our observations and enable more sophisticated theoretical models. Creative theoretical insights will suggest new ways to test ideas about what might exist beyond our observational reach. This journey won't be linear or predictable. There will be surprises, puzzles, and paradigm shifts along the way. What seems certain today might be revised tomorrow in light of new evidence or theoretical insights. What seems speculative or impossible might eventually become mainstream science. But through it all, the fundamental human desire to understand the cosmos will continue to drive our exploration. This desire isn't just about accumulating facts or testing theories. It's about connecting with something larger than ourselves, about finding our place in the vast cosmic story that began with the Big Bang and continues to unfold today. In this sense, our exploration of the universe's edge and what might lie beyond isn't just a scientific endeavor, but also a deeply human one. It reflects our capacity for wonder, our commitment to rational inquiry, and our ability to transcend the limitations of our immediate experience through observation, experimentation, and theoretical reasoning. As we peer beyond the edge of the universe, using all the tools of modern science to glimpse what might lie beyond our observational horizon, we're participating in one of humanity's greatest intellectual adventures. We're extending a journey of discovery that has spanned generations and cultures, continuously expanding our understanding of the cosmos and our place within it. The edge of the universe remains a frontier, not just of space, but of knowledge. What lies beyond is still a mystery, one that continues to inspire wonder, curiosity, and scientific exploration. As we continue this journey, we can look forward to new discoveries, new insights, and perhaps even new ways of understanding the nature of reality itself. We've embarked on an extraordinary journey together, exploring one of the greatest mysteries in all of cosmology, what might exist beyond the edge of our universe. From the limitations of the observable universe to the possibility of multiple universes, from cosmic anomalies to the shape and ultimate fate of our universe, we've ventured into realms that challenge our understanding and stretch our imagination. Now, as we reach the conclusion of our exploration, let's reflect on what we've learned and consider the profound implications of our cosmic quest. Throughout human history, our understanding of the cosmos has continuously expanded. Ancient cultures imagined a small universe centered on Earth, enclosed by a celestial dome or crystal spheres. The Copernican revolution displaced Earth from the center, making it just one planet orbiting the Sun. Later discoveries revealed that our Sun is merely one star among hundreds of billions in the Milky Way galaxy, which itself is just one galaxy among trillions in the observable universe. Each revelation has expanded our cosmic horizon and transformed our understanding of our place within the grand tapestry of existence. Now we stand at the threshold of perhaps the most mind-expanding possibility yet, that our entire observable universe, with its estimated 2 trillion galaxies stretching across 93 billion light-years, might be just one minuscule fragment of a much larger and more diverse reality. Whether we envision this larger reality as an infinite expanse of space continuing beyond our cosmic horizon, or a vast multiverse containing countless bubble universes with different physical laws, the implication is the same. What we can observe is just a tiny portion of what exists. This perspective represents a profound shift in our cosmic understanding. For most of human history, we assumed that what we could observe encompassed all of reality, or at least most of it. Even when we recognized the vastness of the observable universe, we generally assumed it represented the totality of existence. But modern cosmology suggests otherwise, that the observable universe might be to the full extent of reality what a drop of water is to the ocean. The concept of a cosmic horizon is central to this understanding. Our cosmic horizon isn't a physical boundary, but rather a limit to our observations, determined by the finite age of the universe and the finite speed of light. Beyond this horizon lie regions of space whose light hasn't had time to reach us since the Big Bang. And in the context of an accelerating universe, some regions will remain forever beyond our observational reach, no matter how long we wait or how powerful our telescopes become. This horizon represents a fundamental limitation on our direct knowledge of the cosmos. We cannot observe what lies beyond it, at least not using electromagnetic radiation like light. But this doesn't mean we can't develop theories about what might exist beyond, or look for indirect evidence that could support or challenge these theories. The standard model of cosmology, known as lambda CDM, where lambda represents dark energy and CDM stands for cold, dark matter, provides our current best description of the observable universe. According to this model, the universe began in the Big Bang about 13.8 billion years ago, underwent a period of rapid inflation, and has been expanding ever since, with this expansion now accelerating due to the mysterious influence of dark energy. When we extend this model beyond our cosmic horizon, the simplest assumption is that the universe continues in much the same way. More galaxies, more clusters, more filaments and voids forming the cosmic web, all following the same physical laws we observe within our horizon. This more of the same hypothesis aligns with the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. It looks roughly the same regardless of where you are or which direction you look. But several theoretical frameworks in modern physics suggest more exotic possibilities. Eternal inflation theory proposes that our observable universe is just one bubble in a vast, ever-expanding sea of inflating space where new bubble universes continually form. String theory suggests a vast landscape of possible vacuum states, each representing a different universe with potentially different physical laws. Quantum mechanics, in some interpretations, implies a branching multiverse where every possible outcome of every quantum measurement actually occurs in some branch of reality. These various multiverse theories aren't just philosophical speculations, but emerge naturally from some of our most successful physical theories when they're followed to their logical conclusions. They offer potential explanations for puzzling aspects of our universe, such as the apparent fine-tuning of physical constants that allow for the existence of complex structures, including life. If a multiverse does exist, with different bubbles or branches having different physical properties, the fact that our universe seems fine-tuned for complexity and life might not be so surprising. In a vast ensemble of universes with different properties, we naturally find ourselves in one where the conditions happen to be right for our existence. It's not that the universe was designed for life, but rather that life evolved in a universe where the conditions happen to be suitable. This anthropic reasoning doesn't prove the existence of a multiverse, but it offers a potential naturalistic explanation for what otherwise might seem like an extraordinary cosmic coincidence requiring a designer. In a sense, the multiverse concept shifts the question from, why does our universe have the specific properties that allow for life? To, why does reality include so many different possible universes with different properties? Of course, multiverse theories face significant challenges, particularly regarding their empirical testability. Science traditionally relies on observations and experiments that can be repeated and verified, but other universes in a multiverse might be fundamentally unobservable from within our universe, raising questions about whether such theories can be truly scientific. Yet some versions of the multiverse theory do make potentially testable predictions. If our universe collided with another bubble universe in the past, it might have left observable imprints in the cosmic microwave background radiation. Certain quantum gravity theories suggest that other universes might leave subtle signatures in the statistics of galaxy distributions or in the polarization of the CMB. Specific models of cosmic inflation predict particular patterns of primordial gravitational waves that might be detected by future observatories. While evidence for a multiverse remains elusive, the search continues, illustrating how even seemingly metaphysical questions can sometimes be approached scientifically. This ongoing quest reflects one of the most remarkable aspects of human consciousness: our ability to transcend the limitations of our direct experience through observation, experimentation, and theoretical reasoning. From a philosophical perspective, our exploration of what might lie beyond the edge of the universe touches on profound questions about the nature of reality, the limits of knowledge, and our place in the cosmos. Throughout history, philosophers have grappled with questions about the finite or infinite nature of the universe, the possibility of multiple worlds, and whether reality extends beyond what we can directly perceive. The pre-Socratic philosopher Anaximander proposed that our world is just one among many worlds that are born and die over infinite time. The ancient Greek atomists, including Democritus and Epicurus, suggested the existence of infinite worlds in infinite space. In the 16th century, Giordano Bruno argued for an infinite universe containing innumerable worlds, some potentially harboring life, a perspective that contributed to his conviction for heresy and subsequent execution. Modern cosmology brings these ancient philosophical questions into a scientific context, where mathematical models and indirect observations provide ways to reason about what might exist beyond the limits of direct perception. The dialogue between philosophy and science continues today, with each informing and enriching the other as we grapple with the implications of our expanding cosmic understanding. This expanding understanding has repeatedly challenged our sense of centrality and uniqueness. Each major advance in cosmology has revealed that what we previously thought was everything is actually just a small part of a much larger whole. Earth is not the center of the cosmos. The Sun is not the center of the galaxy. The Milky Way is not the only galaxy. And now, our observable universe might not be the entirety of reality. Some might find this progression humbling or even disheartening, a series of cosmic demotions that diminish our significance. But another perspective sees it as liberating and awe-inspiring. We are connected to a reality far vaster and more extraordinary than our ancestors could have imagined. We are part of a cosmic story that might encompass not just one universe, but a multitude, unfolding across scales of space and time that boggle the human mind. This perspective doesn't diminish the wonder of our existence, but rather enhances it. In a potentially infinite multiverse encompassing all possibilities, the particular combination of physical constants, cosmic history, and evolutionary pathways that produce conscious beings capable of contemplating the cosmos would be just one of many possibilities. Yet it's the one we experience because we couldn't exist otherwise. The atoms in our bodies were forged in the hearts of ancient stars that exploded billions of years ago, scattering their enriched material across space to eventually form planets and ultimately life. The carbon, oxygen, nitrogen, and other elements essential for our biology were created through nuclear fusion in stellar cores and supernovae. In a very real sense, we are made of stardust. The universe becoming conscious of itself, this connection to the cosmos transcends whatever might lie beyond our observable horizon. Whether the universe is infinite or finite, whether a multiverse exists or not, we are indisputably linked to the stars and galaxies we can see. Our very existence represents one way that the universe has organized matter into structures complex enough to contemplate their own origins. As we look to the future of cosmic exploration, new telescopes, observatories, and experimental approaches promise to reveal aspects of the universe that are currently hidden from view. The James Webb Space Telescope peers farther back in time than any previous instrument, potentially showing us the first galaxies that formed after the Big Bang. Gravitational wave observatories detect ripples in space-time from colliding black holes and neutron stars, giving us a new way to hear cosmic events that might otherwise remain invisible. Future technologies might push these boundaries even further. Space-based gravitational wave detectors like LISA will be able to detect signals from the early universe, potentially revealing clues about cosmic inflation and what came before the Big Bang. Neutrino observatories might detect the cosmic neutrino background, showing us the universe as it was just 1 second after the Big Bang, much earlier than we can see with light. These observational advances will be complemented by theoretical developments. The quest for a theory of quantum gravity, a unified description of gravity and quantum mechanics, continues to inspire various approaches, including string theory, loop quantum gravity, and others. Such a theory might reveal how space and time behave under the extreme conditions of the early universe or black holes, potentially transforming our understanding of cosmic origins and structure. Computational tools, including artificial intelligence and quantum computing, will enhance our ability to analyze cosmic data and simulate complex physical processes. These tools might reveal patterns in astronomical observations that would be missed by human analysis alone, or enable simulations of cosmic evolution under different theoretical frameworks, allowing us to compare predictions with observations. Through this ongoing scientific exploration, we'll continue to refine our understanding of the universe and what might lie beyond its observable boundaries. Some theories will be supported by new evidence, others will be modified or abandoned. New observations might reveal unexpected phenomena that require novel explanations. The interplay between theory and observation will drive progress, just as it has throughout the history of science. But even as our scientific understanding advances, some aspects of cosmic reality might remain permanently beyond our full comprehension. The accelerating expansion of the universe means that regions beyond our current cosmic horizon will never become visible to us, no matter how long we wait or how powerful our instruments become. Some questions about the ultimate nature of reality might exceed the capabilities of the scientific method, touching on realms where empirical verification is impossible, even in principle. This doesn't mean we should stop exploring. The history of science is full of examples where phenomena that seemed unobservable or incomprehensible were eventually brought within the realm of scientific understanding through ingenious experimental approaches or conceptual breakthroughs. What seems beyond reach today might become accessible tomorrow through advances in technology or theoretical insight. Moreover, the journey of discovery is valuable in itself, regardless of whether we ever reach a complete understanding of what lies beyond the edge of the universe. Each advance in our cosmic knowledge enriches our perspective and deepens our appreciation for the extraordinary reality in which we live. Each new observation or theoretical insight becomes part of the growing tapestry of human understanding, connecting us to a tradition of cosmic exploration that spans cultures and generations. This tradition reflects something fundamental about human nature: our capacity for wonder, curiosity, and the pursuit of knowledge beyond immediate practical concerns. From the earliest skywatchers who tracked the movements of planets to modern cosmologists mapping the large-scale structure of the universe, humans have been driven by a desire to understand the cosmos and our place within it. This desire isn't just about accumulating facts or testing theories, it's about meaning and context. By understanding the universe and what might lie beyond, we gain perspective on our own existence. We see ourselves as part of a cosmic story that began with the Big Bang and continues to unfold today. A story in which the emergence of consciousness represents one of the most remarkable developments in the universe's 14 billion year history. Within this vast cosmic context, our lives take on new significance. We're not just isolated individuals existing for a brief moment in time, but participants in an ongoing cosmic drama, carriers of the universe's consciousness, capable of comprehending the very processes that created us. Our scientific exploration of the cosmos isn't separate from our humanity, but an expression of it, a manifestation of our inherent curiosity, creativity, and drive to understand. As we stand at the edge of the observable universe, peering outward with our telescopes and inward with our mathematical models, we're engaging in one of humanity's most profound endeavors. We're pushing the boundaries of knowledge, expanding our cosmic perspective, and grappling with questions that touch on the deepest mysteries of existence. What lies beyond the edge of the universe? The answer remains incomplete and provisional, subject to revision as our understanding evolves. Perhaps there's more of the same, an infinite expanse of space filled with galaxies similar to those we can observe. Perhaps there's a vast multiverse containing countless bubble universes with different physical laws. Perhaps there are dimensions or aspects of reality that we haven't yet imagined, awaiting discovery through future scientific breakthroughs. Whatever the case, the exploration continues, driven by the same cosmic curiosity that has guided human inquiry for thousands of years. Each generation builds upon the discoveries of those who came before, gradually expanding our understanding of the universe and what might lie beyond its horizon. This ongoing journey of discovery connects us to both our past and our future, to the long history of human cosmic exploration and to the generations yet to come who will continue this quest. As we conclude our exploration of what lies beyond the edge of the universe, we're left not with definitive answers, but with a deeper appreciation for the magnitude and complexity of the questions. We've seen how modern cosmology has transformed our understanding of the universe's structure, history, and potential future. We've considered the possibility that our observable universe might be just one small part of a much larger and more diverse reality. And we've reflected on the philosophical implications of these cosmic perspectives for our understanding of ourselves and our place in the cosmos. The edge of the universe isn't just a physical boundary, but a horizon of knowledge, a frontier that recedes as we approach it, revealing new vistas and new questions with each advance. Beyond this horizon lies the unknown, the unobserved, the theoretical, a realm that continues to inspire wonder, curiosity, and scientific exploration. In a sense, what lies beyond the edge of the universe is an ongoing question rather than a settled answer, a question that drives us forward in our cosmic quest, challenging us to develop new observations, new theories, and new ways of understanding. It's a question that connects science, philosophy, and the human spirit of exploration, reminding us that our journey to understand the cosmos is not just about what we discover, but about who we become in the process. As we gaze up at the night sky, contemplating the billions of stars and galaxies visible to our telescopes, and the potentially infinite realms that lie beyond our cosmic horizon, we participate in a tradition of wonder that spans human history. We see ourselves as both insignificant motes in an incomprehensibly vast cosmos and remarkable beings capable of comprehending that vastness, ephemeral patterns of stardust that have, through the long course of cosmic evolution, developed the capacity to contemplate their origins and their place in the universe. This dual perspective, humility before the cosmic scale, and wonder at our capacity for understanding, guides our ongoing exploration of the universe and what might lie beyond its edge. It reminds us that we are both tiny fragments of the cosmos and conscious participants in its unfolding, both limited in our direct perceptions and boundless in our capacity to transcend those limitations through science, mathematics, philosophy, and imagination. The question of what lies beyond the edge of the universe thus becomes not just a scientific inquiry, but a human one, a question that challenges us to expand our thinking, deepen our understanding, and embrace the profound mystery and wonder of existence. It's a question that has no final answer, but rather an evolving response that grows richer and more nuanced as our knowledge advances and our perspective widens. In this sense, our exploration of cosmic boundaries is also an exploration of human potential, our capacity to transcend the apparent limitations of our physical existence through our minds, to comprehend realms and scales far beyond our direct experience, and to find meaning and context in our connection to the vast cosmic whole. As we conclude this journey exploring the edge of the universe, we carry forward this legacy of cosmic inquiry, a legacy that stretches back to the first humans who looked up at the night sky with wonder, and continues through all those who seek to understand the nature of reality and our place within it. We stand at a remarkable moment in this ongoing quest, with unprecedented tools and insights to help us peer beyond the cosmic horizon and contemplate what might lie in the unseen realms beyond. Whatever we might find in these unexplored cosmic territories, whether infinite space filled with galaxies, a vast multiverse of bubble universes, or something we haven't yet imagined, the journey itself represents one of humanity's greatest achievements. It's a journey that connects us to the stars from which we came, and to the vast, mysterious cosmos of which we are a part. The universe has no edge in the conventional sense, no boundary where space simply ends, no cosmic shoreline beyond which nothing exists. But it does have horizons of observation and understanding, frontiers that challenge us to look farther, think deeper, and imagine more broadly than ever before. Beyond these horizons lies the next chapter in our cosmic story, a chapter we continue to write through our ongoing exploration of the universe and its ultimate nature. As we peer toward these cosmic horizons, we're reminded of the words of the astronomer Maria Mitchell, who wrote in the 19th century, "We have a hunger of the mind which asks for knowledge of all around us, and the more we gain, the more is our desire. The more we see, the more we are capable of seeing." This hunger for knowledge, this desire to understand what lies beyond, continues to drive our cosmic exploration, a journey without end, but with countless wonders and discoveries along the way. In the end, what lies beyond the edge of the universe might remain partially unknown, a mystery that inspires rather than frustrates, that draws us forward rather than limits us. But through our scientific exploration, philosophical reflection, and human imagination, we continue to expand the boundaries of our understanding, revealing an ever more complex, fascinating, and awe-inspiring cosmic reality. The edge of the universe isn't a destination we'll ever fully reach, but a horizon that continually expands as we journey toward it. And in this ongoing journey, this quest to understand the cosmos and our place within it, we find not just scientific knowledge, but also meaning, wonder, and a profound sense of connection to the vast universe from which we emerged and to which we belong. As we look up at the night sky, seeing the stars and galaxies that populate our observable universe, and imagining the unseen realms that might lie beyond, we're participating in one of humanity's most enduring endeavors, the quest to understand the nature of reality itself. This quest continues, driven by our insatiable curiosity about what lies beyond the current limits of our knowledge, beyond the edge of the visible universe, in the vast cosmic domains that await our discovery. The story of the universe isn't complete, nor is our understanding of it. Both continue to evolve, the universe through its ongoing expansion and development, and our understanding through the advancement of science and human thought. What lies beyond the edge of the universe remains an open question, one that will continue to inspire exploration, speculation, and wonder for generations to come. In this ongoing exploration, we find not just answers, but also new questions, not just knowledge, but also mystery, not just facts, but also meaning. The edge of the universe represents not the end of our cosmic journey, but rather its endless horizon, a frontier that recedes as we approach it, continuously revealing new aspects of the extraordinary reality in which we live. As we conclude our exploration of what lies beyond the edge of the universe, we're left with a deeper appreciation for both the vastness of the cosmos and the remarkable human capacity to comprehend it. We've seen how our understanding has evolved from a small, Earth-centered universe to a potentially infinite multiverse. We've considered how modern science allows us to peer beyond our cosmic horizon through indirect evidence and theoretical models, and we've reflected on the philosophical implications of these cosmic perspectives for our understanding of ourselves and our place in existence. The quest to understand what lies beyond the edge of the universe continues, a quest that connects us to both the stars from which we came and to the fundamental human desire to understand our cosmic context. In this ongoing journey of discovery, we find not just scientific knowledge, but also wonder, meaning, and a profound sense of connection to the vast and mysterious cosmos of which we are a part. The edge of the universe isn't a place but a concept, a horizon of understanding that expands as our knowledge grows. Beyond this horizon lies the unknown, the unexplored, the theoretical, a realm that will continue to inspire wonder, curiosity, and scientific exploration for as long as humans gaze up at the stars and ask, what lies beyond?